Hello there and welcome to Science for Sleep, where curiosity is invited to curl up and rest while we wander gently through the universe together. Tonight we're taking a journey into something that stretches far beyond the horizon, far beyond the line of sight, and yet feels like it belongs to us in the most personal way. We're going to talk about our home galaxy, the Milky Way, and try to understand the question that seems simple at first, but unravels into something endlessly fascinating the more you think about it. Just how big is our galaxy? When you step outside at night and look up at a clear sky, perhaps in a quiet place away from the city lights, you might notice a pale streak stretching from one end of the heavens to the other. It looks like a soft band of mist or a brushstroke across the darkness. That band is the Milky Way itself, the combined glow of billions of stars so distant and so numerous that our eyes can't separate them. They blur into a shimmering haze, the edge-on view of the vast disk we live inside. For countless generations, people have looked at that glow and wondered what it really is. Stories have been told about it, myths spun, paths named after it, but now we can measure it, map it, and begin to sense its scale. And yet, even with all our instruments, it's still hard to grasp. Before we wade too deeply into numbers, I'd like to ask you something. Where are you listening from right now? Are you in a city where the glow of street lamps drowns out all but the brightest stars? Are you somewhere rural where the Milky Way is still bold, a ribbon of light arcing overhead? Maybe you're indoors, cozy and quiet, with only the thought of the night sky in your imagination. Wherever you are, you're already inside this immense structure we're about to explore. You're not just watching from outside, you're a passenger travelling within it, carried along on a tiny planet orbiting a modest star that itself is part of a grand spiral pattern. If you find this little voyage comforting, soothing, or a nice way to let the day dissolve, I'd be grateful if you gave this a like or maybe subscribed. It helps this quiet corner reach others who might also want a calm place to settle their thoughts, and perhaps tonight it will even help you drift off while still holding on to the wonder of the cosmos. Don't worry, you don't need to remember every detail. Just let the scale of it all flow past, like listening to the tide. So let's begin by grounding ourselves in something familiar. You know Earth. It feels vast when you think of oceans stretching thousands of kilometres, continents that take hours to cross by plane. Yet Earth is tiny compared to the Sun. About 100 Earths could line up across the Sun's face. Our star, which seems so steady and central to our lives, is itself one of hundreds of billions in the Milky Way. And the Sun is not particularly special in size or brightness. It's somewhere in the middle, a star of average output, orbiting quietly through the galaxy's disk. If you could somehow shrink Earth down to a grain of sand and place it on a beach, the Sun would be a ball about the size of a grapefruit next to it. Now, imagine billions upon billions of grapefruits scattered across an entire continent, and you begin to get an intuition for the population of stars around us. The Milky Way contains somewhere between 100 and 400 billion stars, depending on how you count them, and possibly even more if faint small stars are included. That number alone is staggering, but the real question is how much space they all occupy. The disk of the Milky Way is about 100,000 light-years across, give or take, depending on which measurement you look at. That means if you could somehow travel at the speed of light, the fastest speed the universe allows, it would still take you 100,000 years just to get from one side of the disk to the other. And remember, that's not a leisurely pace. That's at light speed. For comparison, light from the Sun takes about 8 minutes to reach Earth. Imagine those 8 minutes stretched into 100,000 years, and you start to sense the immensity of the galaxy's span. But even a number like 100,000 light-years is difficult to wrap your head around, isn't it? Our everyday sense of distance is built on car rides, plane flights, or maybe the occasional intercontinental journey. A kilometre, 100 kilometres, perhaps a few thousand. These are the ranges we know. Even when we say millions, it still feels human. A million steps, a million grains of rice. but a light year is already beyond anything intuitive. 1 light year is about 9.5 trillion kilometres. If you tried to drive a car at highway speed, say 100 kilometres per hour, and kept driving non-stop day and night, it would take you over 10 million years to cross a single light year. Multiply that by 100,000, and you begin to see why the Milky Way feels like a realm that stretches into the unimaginable. The Sun, carrying Earth along with it, orbits the centre of the Milky Way at a speed of about 828,000 kilometres per hour. That sounds fast, but the galaxy is so vast that it takes about 225 to 250 million years to complete a single orbit. That means in the entire history of humanity, from the first stone tools to space telescopes, our solar system hasn't even made a fraction of one full circle around the galactic centre. Dinosaurs were walking the Earth the last time the Sun was in roughly the same place in its orbit as it is now. So when you think about scale, it's not just the size of the galaxy across, but also the time it takes to move within it. As we explore further, keep in mind that size is not just a matter of physical distance, it's also a matter of structure and content. The Milky Way isn't just a flat disk like a dinner plate, it has thickness. The thin disk where most of the stars lie is about 1,000 light years thick. But beyond that, there's a thicker disk and a halo of stars, globular clusters, and dark matter extending far beyond. The halo might reach 300,000 light years or more from the centre, which means the true size of the Milky Way depends on how you define the edge. There isn't a sharp boundary. It just fades outward, stars becoming sparser, until at some point they're more influenced by neighbouring galaxies than by our own. The very term Milky Way carries a sense of softness, like something poured across the heavens. In Greek mythology, it was said to be milk spilled from the goddess Hera. In China, it was the river of heaven, separating two lovers who could only meet once a year when magpies formed a bridge. In Finland, it was the pathway of birds. Cultures everywhere gave it names, always with a sense of mystery, because the human eye could see its brightness but not its individual stars. Now we know that brightness is the light of billions of suns blurred together, and that alone gives a clue to its immensity. If you could isolate just a patch of sky as wide as the moon, and count every star within the Milky Way in that patch, you'd find thousands. Spread across the entire band, multiplied across the full disk, the numbers climb to the billions. Yet size isn't just measured in stars. Between them lies gas, dust, and dark matter. Vast clouds of hydrogen stretch across light years, collapsing in places to form new stars. Dust grains, smaller than a fraction of a human hair, clump together in enormous bands that absorb starlight and create the dark patches you can sometimes see streaking through the Milky Way's glow. These clouds make it harder to see the far side of the galaxy. For a long time, astronomers didn't even know exactly what shape the Milky Way had because we're stuck inside it, looking through all that material. Only by measuring the positions of stars, mapping radio signals from hydrogen gas, and now using space telescopes like Gaia that chart stellar motions with incredible precision, have we been able to build a clearer picture. And still, there are uncertainties. When you ask how big is our galaxy, the answer depends on what you include. The visible disk of stars, the extended halo of old clusters, the invisible but gravitationally powerful dark matter that may outweigh all the stars combined. If you count everything, the Milky Way's true extent could be closer to 1 million light-years across, though the densest part, the familiar glowing band, is nearer to 100,000. Both numbers are true in their own way, depending on perspective. The challenge is that human intuition wasn't built to handle such sizes. We evolved to notice whether the next hill had fruit trees, or whether the next valley had water. Our brains are good at grasping meters, maybe kilometers. When the scales stretch to thousands of trillions of kilometers, we need metaphors. Imagine shrinking the entire Milky Way to the size of a dinner plate. In that case, our entire solar system from the Sun out to Pluto and beyond would be smaller than a grain of sand. That's how tiny our neighbourhood is compared to the full galaxy. Thinking about this scale can feel overwhelming, but it can also be strangely comforting. The galaxy is so large, so enduring, that our worries and stresses shrink by comparison. The things that feel enormous in a single day or week become tiny in the perspective of hundreds of thousands of light years and hundreds of millions of years of galactic orbits. It's like listening to the tick of a small clock while knowing that beyond the room lies the ocean. The clock is real, the ocean is vast, and both exist together. Even with modern astronomy, we're still uncovering details about the galaxy's size. Surveys like Gaia are mapping billions of stars, creating the most precise 3D model ever made of the Milky Way. With each update, distances are refined, the shape of spiral arms becomes clearer, and our understanding of the galaxy's mass grows. Right now, estimates suggest the Milky Way's mass is about 1 to 2 trillion times the mass of the Sun, most of that in dark matter. That mass influences not only the stars inside, but also the smaller galaxies orbiting around us, like the Magellanic Clouds, and even our future collision course with the Andromeda Galaxy billions of years from now. So when we talk about how big the Milky Way is, we're really asking several questions at once. How many stars does it contain? How wide is the disk? How far does the halo extend? How much mass is hidden in dark matter? How long does it take for stars to orbit the centre? Each question gives a slightly different answer, but together they paint the picture of a structure so large that human words struggle to contain it. And yet, you're part of it. Not outside, not separate, but inside this galaxy. Every breath you take, every heartbeat, every thought happens while circling the galactic centre, moving at hundreds of thousands of kilometres per hour. You're riding the spiral arm of the Milky Way, a passenger in a system of unimaginable scale, and that thought alone can carry you deeper into curiosity or perhaps into sleep. When you step outside on a clear night and let your eyes adjust to the darkness, you might notice a faint arch stretching across the sky. It doesn't look like individual stars. Instead, it resembles a pale river, wide and hazy, running from one horizon to the other. That is the Milky Way as seen from inside, and it's one of the most striking sights available to the naked eye. People who have grown up in cities with heavy light pollution might never have seen it in its full clarity. Street lamps and neon signs drown out the faint glow, leaving only the brighter stars behind. But in dark sky regions, far from artificial lights, the sight can take your breath away. The band of the Milky Way has inspired myths, guided travellers, and puzzled philosophers for thousands of years. Today we know that what looks like a milky river is actually the combined light of billions of distant stars, smeared together by the limits of our vision. Imagine trying to count grains of sand on a beach, but from so far away that all you can see is a continuous blur. That's what the Milky Way looks like to our eyes. Each tiny speck of that glow is a star system, many with planets of their own, scattered across the disk of the galaxy. We are embedded in one of the spiral arms, so what we're really seeing is the edge-on view of our galactic home. When you look at the Milky Way stretching across the night, you are gazing through the densest part of the disk, through layers upon layers of stars, gas and dust. The ancient Greeks thought this glowing path was milk spilled across the heavens. That's where the name Milky Way comes from. In India, it was sometimes called the Ganges of the sky, a celestial river flowing above Earth's own. In the Americas, some indigenous peoples saw it as a trail of spirits. Each culture gave it a name that reflected how it appeared to them and how it fit into their world. Long before telescopes, before photography, people could only guess at what it was. Some thought it was fire, others thought it was the seam where the sky itself was stitched together. The unifying factor is that everyone who saw it recognized it as something immense, beyond ordinary experience. When Galileo turned one of the first telescopes to the Milky Way in the early 1600s, he discovered that the hazy band resolved into countless stars. This was one of the earliest moments when humanity realized that the faint glow in the sky was not a cloud or vapor, but the light of innumerable suns. Since then, every new instrument has added detail. Larger telescopes revealed structure. photographic plates captured faint regions invisible to the eye. Radio astronomy mapped the hydrogen gas spread across the disk. Infrared telescopes pierced through dust clouds. Space telescopes measured stellar positions with exquisite accuracy. Together, these views built the picture we now have of a spiral galaxy with sweeping arms, a central bulge, and a halo of stars surrounding it all. Still, standing outside under the night sky, you don't need advanced equipment to sense the vastness. The Milky Way arches overhead as a reminder that we live inside something far bigger than ourselves. You're looking into the thickness of the disk, seeing light that has travelled tens of thousands of years to reach your eyes. That means every time you glance at the Milky Way, you're receiving messages from the deep past. The stars whose glow you see may not even exist anymore. Some may have burned out or exploded long before the first humans walked the Earth, but their light is only arriving now. The galaxy is not just vast in size, but in time. The river-like appearance is enhanced by dark lanes running through it. These are regions of dense interstellar dust that block light from stars behind them. To the naked eye, they look like ragged gaps, like torn cloth across the glow. In reality, they are cold clouds of dust and gas where new stars may one day form. These regions are nurseries, hiding the birth of new systems. Through a telescope, the Milky Way reveals clusters of young blue stars, glowing nebulae and older red giants. It is not uniform. It is a landscape full of variety, each patch telling a slightly different story of stellar evolution. The sheer number of stars is difficult to comprehend. Imagine standing in front of a city skyline at night, every window lit up. Now multiply that by thousands, then tens of thousands, and you begin to approximate what's contained in a single sweep of the Milky Way. When astronomers attempt to count stars, they use statistical estimates. No one can tally each one individually. Instead, they measure the density in one region and extrapolate. That's how we arrive at figures of 100 to 400 billion stars. And yet, the Milky Way may also contain billions of planets, perhaps more planets than stars, if smaller rocky worlds like Earth are common. So when you look up and see that Milky Band, you're not just seeing stars, you're glimpsing a galactic ocean of worlds. What makes the Milky Way so visible to the naked eye is not just the stars themselves, but the way they overlap. Individual stars appear as points of light, but collectively they blend into a glow. Your eyes cannot resolve them separately. That blur is a measure of scale. The faint glow is billions of light-years of photons, packed tightly enough that they merge in your vision. It's a natural demonstration of crowding at a cosmic level. The width of the band depends on where you are on Earth. Near the equator, the Milky Way stretches nearly overhead, a clear arch from horizon to horizon. In higher latitudes, you see it tilted or lower on the horizon. At certain times of year, the core region, which is densest and brightest, becomes visible. That's toward the constellation Sagittarius. In those months, the Milky Way looks especially rich, with a swelling of brightness where the galactic centre lies. This region is crowded with stars, nebulae, and, hidden at the very centre, a supermassive black hole called Sagittarius A. Of course, none of that is visible to the naked eye, but the increased brightness gives a clue to the structure. The Milky Way is not unique in its appearance. If you could step outside the galaxy and look at it from far away, it would resemble other spiral galaxies we see through telescopes. Galaxies like Andromeda, or the Whirlpool Galaxy, show us what our own might look like if we had an external vantage point. A glowing disk with spiral arms, a bright bulge in the centre, and faint extensions stretching outward. From Earth, though, we only ever see it from within, as a band above us. That limitation is part of why it took so long for astronomers to understand its full shape. For much of history, people thought the Milky Way was the entire universe. The idea that there were other galaxies beyond it was not widely accepted until the early 20th century. When astronomers like Edwin Hubble demonstrated that spiral nebulae were actually entire galaxies far outside the Milky Way, the scale of everything expanded. What we'd called the universe became just one galaxy among billions. And yet, the Milky Way remained our home, our river of light in the sky. Its vastness did not shrink when compared to the universe. Instead, it gained context, a sense of belonging within something even larger. It's worth pausing to think about how we perceive that band compared to what it actually is. When you look at the Milky Way, you're not seeing the whole galaxy. You're seeing the densest slice of the disk, the part where the line of sight passes through the greatest number of stars. You're looking edge on. If we could see the galaxy face on, it would appear as a grand spiral. From inside we get only the side view, like standing in a forest and looking between the trunks of countless trees. The forest feels endless, but you're only seeing along one line. The river analogy is fitting in another way. Just as a river carries water downstream, the Milky Way carries stars, gas and dust in orbit around its centre. Everything you see in the night sky, every star visible to your eyes, is part of this great flow. We are immersed in it, carried along without choice, orbiting the galactic core. The sense of motion is too slow to feel directly, but over millions of years, the galaxy's river shapes the destiny of stars and worlds alike. The brightness of the Milky Way also changes with altitude. In the mountains, above the haze of the atmosphere, the band appears sharper and more detailed. Astronomers have long sought high, dry places for their observatories to reduce distortion from the air. That's why telescopes are built on peaks in Chile, Hawaii, or the Canary Islands. From there, the Milky Way reveals itself more clearly, and even faint features become visible. Yet the basic sight, that glowing band, is available to anyone willing to step outside in darkness. It is one of the few cosmic spectacles visible without equipment. The first time someone sees the Milky Way clearly can be transformative. For city dwellers, the sight can feel overwhelming. Some even report discomfort, a kind of vertigo, when confronted with so many stars. Psychologists call this the overview effect, when astronauts describe the emotional impact of seeing Earth from space. A similar reaction can occur when people realize they are inside a galaxy filled with billions of suns. It's a mixture of awe, humility, and sometimes unease. But mostly it's wonder. That wonder has driven humanity to ask questions, to build instruments, and to seek understanding. What's striking is that no matter how much we learn, the Milky Way still inspires the same feelings it did centuries ago. Knowing that the band is billions of stars does not make it less beautiful. If anything, it makes it richer. The glow above you is not just a pretty sight, it's evidence of structure on the grandest scales. It's a reminder that you are part of something immense. And the river stretches endlessly. It crosses the sky in silence while we turn beneath it. Every rotation of Earth brings different sections into view. The Milky Way is always there, but we see it from changing angles, different seasons, different times of night. That slow shifting gives rhythm to our lives. Farmers once used the positions of stars along the band to mark seasons. Sailors navigated by it. Today, even with GPS and digital clocks, the Milky Way still shines as a marker of time and place. It is vast not only in distance, but also in history. The stars that form its glow range from newborns a few million years old to ancient ones older than 10 billion years. Some shine blue and hot, destined to burn out quickly. Others glow red and cool, fated to endure for trillions of years. Together they form a population that tells the story of the galaxy's past and hints at its future. To see the Milky Way is to see billions of timelines at once, each star with its own lifespan, each light a different chapter in the galactic narrative. And so, when you look up and see that river of light, remember that you are not separate from it. You are inside it. The atoms in your body, the breath you just took, the thoughts passing through your mind, all are happening within this immense structure. You're one of countless beings living in one of countless systems, part of the river itself. If you've ever tried to count stars on a clear night, you know how quickly the task overwhelms you. You pick a section of sky, start pointing out the brighter ones, and soon realise there are dozens more hiding in the background. By the time you've reached a few hundred, your eyes start slipping and the numbers blur. Even in the darkest skies, the human eye can see only a few thousand stars at most. That might sound like a lot, but compared to the true number of stars in the Milky Way, it's barely a handful. Our galaxy contains hundreds of billions, perhaps even more if faint red dwarfs are as common as we think. When astronomers say hundreds of billions, they don't mean someone has sat down and tallied each one. The numbers come from estimates, built carefully from observations. The first step is to measure the density of stars in a given patch of sky. Then, using the knowledge of how bright different stars are and how far away they sit, astronomers scale up. It's a bit like walking into a forest, counting trees in a single clearing, and then multiplying by the size of the forest. The method isn't perfect. Some regions are hidden behind dust clouds, others are crowded beyond easy resolution, but with modern telescopes, especially space-based ones that can see in wavelengths beyond visible light, the estimates have become more reliable. Counting stars isn't just an exercise in numbers, it's also a way of asking what kind of galaxy we live in. A galaxy's size and brightness are defined not only by how wide it is, but by how many stars it holds. The Milky Way, with its hundreds of billions, is considered a large spiral galaxy, though not the largest in the universe. Other galaxies, like Andromeda or the giant ellipticals found in galaxy clusters, may hold 1 trillion stars or more. But for us, the Milky Way is home enough, immense enough that its population is beyond comprehension. To put the numbers in perspective, let's imagine each star in the galaxy as a single grain of sand. If you were to collect 100 billion grains, you'd have enough to fill several Olympic-sized swimming pools. Spread across a beach, the collection would stretch for kilometres. Now picture trying to count those grains one by one. That's the scale of stars in the Milky Way. And yet, when astronomers map them, they don't just think in terms of grains. Each star is a sun, with the potential for planets, moons, and maybe life. Counting stars is counting possibilities, each one a dream of worlds we may never see but know must exist. The question of how many stars exist has fascinated people for centuries. The philosopher Democritus, living more than 2,000 years ago, speculated that the Milky Way was made of countless distant suns. Others thought it was a cloud or fire or even a seam in the sky. It wasn't until Galileo's telescope that the truth began to emerge. Today, modern surveys like the Gaia mission chart billions of stars with precise positions and motions. Gaia has already measured more than 1 billion stars, creating a detailed 3D map of our corner of the galaxy. Even that astonishing number is still less than 1% of the total. We have a census in progress, but the vast majority remain uncounted, glowing far away in the disk or hidden in clouds. What's striking is how unevenly the stars are distributed. Near the galactic centre, stars are packed densely, sometimes so close that from a planet there the night sky would be ablaze with brightness. Out near the edges, stars are more scattered, separated by great distances. Our sun lies somewhere in between, in a relatively calm neighbourhood. From our vantage point, the stars look spread evenly, but that's an illusion of distance. In reality, clusters form, associations gather, and spiral arms weave concentrations together. Counting stars is not just arithmetic, it's a way of reading the galaxy's structure. Some stars are giants, tens or hundreds of times more massive than the Sun. They burn brightly and live briefly, sometimes only a few million years before exploding in supernovae. Others are small red dwarfs, cooler and dimmer, capable of living for trillions of years. Most of the stars in the galaxy are in this latter category, faint and hard to see, but numerous beyond belief. They are the background population, the quiet majority. If you were to count only the bright stars visible to the naked eye, you would be missing the overwhelming bulk of the galaxy's inhabitants. To know the true size, astronomers must account for the unseen. There are also binary stars, systems where two suns orbit each other. In fact, more than half of all stars are in multiple systems, not alone like the Sun. triple systems, quadruple systems, and more exotic arrangements exist. Each of those stars counts toward the total, and each has its own orbit and story. When astronomers tally the galaxy, they're counting not just individuals but families, whole groups locked together by gravity. And when you imagine planets orbiting these stars, you begin to realise the sheer variety of environments possible. Counting stars is also counting history. The oldest stars in the Milky Way are more than 13 billion years old, almost as old as the universe itself. They live mostly in the halo, in globular clusters, shining faintly with the chemical fingerprints of the early cosmos. Younger stars, like those in the spiral arms, formed from gas enriched by generations of supernovae. By measuring the age distribution, astronomers can trace how the galaxy built itself over billions of years. Each star is a data point in a timeline, a marker of when and where formation occurred. In this sense, counting stars is like counting rings in a tree, revealing the growth of something vast and ancient. Yet despite the science, there is something deeply human about the attempt to count. Children lying under the stars often try it, pointing one by one until they lose track. There's a dreamlike quality to it, as if by naming or numbering the stars we could grasp the infinite. Ancient cultures gave names to constellations, drawing patterns and stories among the lights. Farmers marked seasons by rising stars. Navigators followed them across oceans. Each point of light became more than just physics. It became part of a shared human story. Counting stars was counting meaning, and when you think about the galaxy as a whole, the dream expands. If there are hundreds of billions of stars and many of them have planets, how many worlds must be out there? Some are barren, scorched or frozen. Some may be rich with oceans or clouds. Perhaps a few host life. Perhaps somewhere, intelligence looks back at its own sky and wonders how many stars exist. Counting stars is not just about quantity. It is about asking how many chances there are for company. How many dreams may be happening simultaneously across the galaxy? Astronomers use a variety of methods to refine their counts. Infrared surveys peer through dust to reveal hidden stars. Radio telescopes trace hydrogen gas, showing where new stars are forming. Stellar populations are modelled using computer simulations that test how stars evolve and die. All of this helps estimate not only how many stars exist now, but how many have existed over the galaxy's lifetime. Stars are born and die constantly. The galaxy is not static. It is a living system, recycling material, forging new generations. Counting stars is therefore not a single number, but a dynamic process, always changing, always in motion. It's easy to forget that our sun is one of those counted stars. To us it feels unique, central, vital. But from the perspective of the galaxy, it is just one among hundreds of billions, ordinary in size, ordinary in brightness, ordinary in its position. And yet, from this ordinary star, extraordinary things arose. Earth formed, life emerged, consciousness grew, and now you sit here listening to thoughts about counting stars. That perspective, that link between the ordinary and the extraordinary, is perhaps the most humbling part of all. Some astronomers and writers compare the number of stars in the Milky Way to the number of grains of sand on all the beaches of Earth. While the analogy isn't perfect, it gives a sense of immensity. If every star were a grain of sand, our galaxy would be a beach stretching beyond the horizon. To stand on such a beach trying to count would be impossible. But just as a beach is made of individual grains, the galaxy is made of individual suns. Each one is real. Each one burns, radiates, and moves through space. The total is unimaginable, but the parts are tangible. The act of counting, then, becomes symbolic. We cannot truly finish it, but we attempt it anyway. It is our way of reaching out into the unknown, of giving shape to the vastness. Children counting stars before sleep. Astronomers tallying with billion-dollar telescopes, both are part of the same impulse. To count is to connect, to bring the unreachable into the realm of thought. And even as the numbers overwhelm, dreams emerge. Each star becomes a story. Each count becomes a possibility. Perhaps somewhere, someone else is counting too, under a different sky, in a different arm of the galaxy. Perhaps they wonder the same things, feel the same awe, ask the same questions. The Milky Way is large enough to hold countless lives, countless stories, countless dreams. So when we ask how many stars there are, we're really asking how vast the possibilities are. The answer, in every sense, is almost beyond measure. But that doesn't mean we stop trying. It means the counting itself becomes part of the wonder. When you think of the Milky Way from the inside, it can be difficult to picture its overall form. We see the band of light stretching overhead, but we can't step outside to look at it from afar. To understand the shape, astronomers rely on observations, mapping star positions, tracing gas clouds, and modelling motion. Through this careful work, a picture has emerged of a spiral galaxy, with sweeping arms, curling outward from a central bulge. These arms are not rigid structures, but regions of higher density, places where stars, gas and dust gather in graceful arcs. They give the Milky Way its character, and they are the features that hold us close within the galactic disk. Our solar system lies inside one of these arms, or more precisely in a smaller spur between two major arms. The Sun and its planets orbit within what's known as the Orion Arm, a minor branch nestled between the larger Sagittarius Arm and Perseus Arm. From here, we look outward across the disk, seeing the accumulated glow of stars along these sweeping structures. The spiral arms are not solid walls of stars. They are more like traffic jams in the galactic highway, regions where material piles up, triggering waves of star formation. Stars move in and out of the arms over time, but the density wave itself persists, slowly winding through the disk. The idea of spiral arms can be confusing if you think of them as permanent features. Instead, they are patterns, like ripples in water or sound waves in air. The material within them changes constantly, but the overall wave travels around the galaxy, shaping where stars are born. The Orion Arm, where we live, is home to familiar constellations. Orion itself, with its belt of 3 bright stars, gives the arm its name. Along with Orion, this region includes the Cygnus and Perseus constellations, parts of Scutum and Carina, and many of the nebulae visible with telescopes. When you see glowing clouds like the Orion Nebula or the Lagoon Nebula, you're looking at nurseries within these spiral structures. The scale of these arms is immense. The Perseus Arm, one of the major structures, lies about 10,000 light-years from our solar system and extends around much of the disk. The Sagittarius Arm, closer to the galactic centre, is rich with star clusters and nebulae. Beyond these lies the Scutum Centaurus Arm, one of the largest and most massive, stretching across the galaxy's interior, and farther out on the rim lies the outer arm, faint and difficult to observe, but still a recognised component of the spiral pattern. Each arm contains billions of stars, rivers of gas, and dust clouds spanning thousands of light years. Astronomers have identified the arms through careful mapping of radio emissions, particularly from hydrogen gas. Hydrogen emits radio waves at a wavelength of 21 centimetres, which can pass through dust clouds that block visible light. By measuring these emissions and their Doppler shifts, scientists can map the structure of the Milky Way even from within. This technique has revealed the winding spiral pattern, though our exact view remains limited. It's like trying to draw a map of a forest while standing among the trees. You see only what surrounds you, but by piecing together many observations, the larger structure becomes clear. One of the most intriguing aspects of spiral arms is their role in star formation. The density waves compress gas clouds, triggering collapse. Massive stars form, burn brightly, and die quickly, often within a few million years. Because of their short lives, these bright stars remain close to where they were born, marking the spiral arms with their glow. Nebulae, clusters, and associations of hot blue stars all trace the paths of the arms, making them visible to astronomers. Meanwhile, smaller stars like the Sun can drift away, living billions of years and scattering throughout the disk. In this way, the spiral arms act as cradles of creation, constantly renewing the galaxy. Our own position within the Orion arm gives us a relatively good vantage point. If we were deeper inside a major arm, the sky might be so bright with stars that it would be difficult to see dark space between them. Here, on the quieter spur, we have a clearer view outward. The night sky as we know it, with its constellations and familiar landmarks, is shaped by our place in this minor arm. It's humbling to realise that our cultural stories, navigational practices, and even our sense of the cosmos are influenced by this galactic address. The arms themselves rotate around the galaxy, but not as rigid structures. Stars closer to the centre orbit faster than those farther out, a phenomenon called differential rotation. If the arms were solid, they would wind up and disappear over billions of years. Instead, the density wave theory explains how the pattern persists. The arms are not collections of the same stars over time, but rather zones where stars appear and fade, much like cars entering and leaving a traffic jam while the congestion remains in place. This dynamic nature makes spiral galaxies both beautiful and complex, structures that balance order and change. In photographs of other galaxies, the arms appear striking, glowing arcs wrapping around bright centres. When you look at the Whirlpool Galaxy or the Pinwheel Galaxy, you're seeing examples of what the Milky Way would look like if we could step outside. These arms are dotted with star-forming regions, glowing with the pink light of hydrogen gas ionized by hot stars. Dark dust lanes thread through them, absorbing light and creating contrast. The similarity of these external galaxies to our models of the Milky Way gives confidence that our understanding is on the right track. Spiral arms are not unique to the Milky Way. They are common features of disk galaxies throughout the universe. Some galaxies have two grand arms, symmetrical and sweeping. Others have multiple fragmented arms, more irregular in shape. The Milky Way falls somewhere in between, with a bar-shaped centre from which arms extend, a structure known as a barred spiral. The bar itself, a concentration of stars stretching across the central bulge, plays a role in channeling gas inward, feeding the core and shaping the dynamics of the inner galaxy. The arms are not just stellar highways, they also influence the future of the galaxy. By concentrating gas, they regulate star formation rates, determining how quickly the galaxy converts material into new stars. Over billions of years, the balance between formation and consumption affects how the galaxy evolves. Too much star formation too quickly, and the gas would run out. Too little, and the galaxy would fade. The spiral arms maintain a steady rhythm, ensuring that stars continue to form across cosmic time. From our perspective on Earth, the spiral structure is not obvious. The Milky Way appears as a band because we see it edge on. The arms are hidden in the thickness of that band. Only by mapping distances and motions do we uncover the spiral. And yet, knowing they are there changes how we look at the sky. Each cluster, each nebula, each region of brightness is a clue to the underlying pattern. The Orion Nebula, visible even to the naked eye as a faint patch, is part of this grand design. It is a stellar nursery within our local arm, a place where the process continues. The sheer size of the spiral arms is staggering. Each stretches thousands of light years across and hundreds of light years thick. Within them, countless suns orbit, each with its own system. Between the arms, the density is lower but still immense by human standards. The distinction is not absolute. Stars move in and out, carrying their planets with them. The arms are less like walls and more like waves, patterns within the larger disk. But for us they define our place in the galaxy, the context in which our solar system orbits. To think of the spiral arms is to think of connection. We are tied to the galaxy not just by gravity but by the patterns that shape it. The arms gather material, birth stars, scatter them, and repeat. We are the products of that cycle, born from material that passed through arms long before the sun existed. Our atoms, forged in earlier generations of stars, are the legacy of countless passages through density waves. Every breath you take, every cell in your body, is linked to the spiral arms that continue to sweep through the galaxy. And the arms keep moving. Over the next hundreds of millions of years, our solar system will drift, carried along by the orbit, encountering new regions, new neighbours, new perspectives on the galaxy. The arms will continue to guide where stars form, where clusters gather, where nebulae glow. They are not static but living features, patterns that endure even as their contents change. To know the spiral arms is to know the heartbeat of the Milky Way, the rhythm by which it grows and evolves. When people think about the Milky Way, they often imagine the glowing band of stars spread across the night sky, but hidden within that brightness is a region that defines the galaxy itself. Deep in the direction of the constellation, Sagittarius lies the galactic centre, a crowded, energetic and mysterious zone that acts as the beating heart of the Milky Way. It is not a place we can see directly with our eyes. Intervening clouds of gas and dust block visible light, making the core invisible to ordinary telescopes. Yet through radio waves, infrared light and X-rays, astronomers have slowly peeled back the obscuring layers, revealing a landscape unlike any other in the galaxy. The centre is about 26,000 light-years from Earth. That means the light and radio waves we detect from it today began their journey long before human civilization arose. When those photons set out, woolly mammoths still roamed the northern plains, and the last ice age was near its end. By the time they reached our telescopes, entire epochs of human history had passed. So when you look towards Sagittarius on a dark night, you're not just facing a patch of stars. You're gazing in the direction of something immense and ancient, a core that has shaped the Milky Way for billions of years. The central region spans only a few hundred light-years across, yet it contains a huge fraction of the galaxy's mass and activity. Stars there are far more densely packed than in our neighbourhood. In the vicinity of the core, a single cubic light-year may contain hundreds, or even thousands of stars. If you lived on a planet there, your night sky would not resemble ours. Instead of seeing a scattered dome of stars, you would see a sky ablaze with countless suns, many bright enough to cast shadows. The familiar constellations would vanish into the glare. The sense of cosmic isolation we sometimes feel would be replaced by a profound closeness, as if the universe itself pressed in on all sides. But the galactic centre is not only dense with stars, it also contains the largest gravitational anchor of them all, a supermassive black hole known as Sagittarius A. This object, with a mass of about 4 million suns, sits at the very heart of the Milky Way. Its presence was confirmed by decades of observations tracking the orbits of stars near the core. Astronomers watched as these stars whipped around an unseen point, completing orbits in mere years. Only an object with immense gravity, concentrated into a tiny region, could explain their motion. In 2022, the Event Horizon Telescope released the first image of Sagittarius A, a blurry yet groundbreaking picture showing the shadow of the black hole surrounded by glowing gas. For the first time, humanity saw the silhouette of the monster that anchors our galaxy. Despite its fearsome reputation, Sagittarius A is surprisingly quiet compared to black holes in some other galaxies. Many galactic centres host active quasars, spewing jets of energy across millions of light-years. Ours, by contrast, is in a relatively dormant state. It does occasionally flare, emitting bursts of X-rays and radio waves as material falls inward, but for the most part it consumes matter quietly. This calmness is fortunate. If Sagittarius A were as active as some black holes, Earth would be bathed in radiation that could disrupt life. Instead, we orbit in peace, distant enough to be unaffected by the core's occasional outbursts. The surrounding region, though, is anything but peaceful. Gas clouds swirl, compressed by gravity and shocks, forming new stars at a rapid rate. The galactic centre is one of the most vigorous star-forming regions in the Milky Way. massive stars, short-lived but brilliant, ignite and explode within a few million years, seeding the environment with heavy elements. Supernova remnants lace the region, their shock waves colliding with other clouds, triggering further collapses. It is a cycle of creation and destruction, condensed into a small volume of space. The energy output of the central region, though mostly hidden from human eyes, is immense. Infrared and radio telescopes have revealed structures with names that sound almost whimsical. The Arches Cluster, the Quintuplet Cluster, the Central Molecular Zone. These are collections of stars and gas packed closer than anywhere else in the galaxy. The Arches Cluster, for example, contains some of the most massive stars known, each dozens of times the mass of the Sun, all crammed into a few light years. Their radiation and stellar winds carve cavities in the surrounding gas, sculpting the environment in chaotic patterns. To us the details are faint signals in detectors, but to an observer near the core the spectacle would be overwhelming. What makes the galactic centre even more fascinating is how it connects to the rest of the Milky Way. The spiral arms all converge there, like spokes into a hub. The bar-shaped structure of stars that stretches across the central bulge channels gas inward, feeding star formation and the black hole. The dynamics of the whole galaxy depend on this inner engine. The motions of stars in the disk, the orbits of satellite galaxies, and the shaping of spiral arms are all influenced by the mass concentrated at the centre. It is the hidden heartbeat, steady and relentless, guiding the rhythm of the galaxy. The core has also played a role in Earth's history, though indirectly. As our solar system orbits the galaxy every few 100 million years, it experiences different regions and conditions. Some scientists have speculated that passing through the denser parts of spiral arms or near the galactic centre could influence the influx of cosmic rays or even perturb comets in the outer solar system. While the evidence for direct effects is debated, it highlights how deeply our lives are tied to the larger motions of the galaxy. Even here, far from the core, we feel its pull. The black hole itself remains an enigma. Though we know its mass and location, many questions linger. How did it form? Did it begin as a smaller black hole in the early galaxy, growing over time by swallowing stars and gas? Or was it born massive, seeded by the collapse of primordial clouds? The answers may hold clues to how galaxies themselves evolve, since nearly all large galaxies host central black holes. The link between galaxy size and black hole mass suggests a deep relationship, as if the heart and the body grow together. Closer to home, astronomers continue to study Sagittarius A with ever-improving tools. Infrared telescopes follow the orbits of individual stars, watching them whip around the black hole at speeds of thousands of kilometres per second. Radio arrays like the Event Horizon telescope capture the glow of hot gas near the event horizon. Future instruments may even detect gravitational waves from interactions near the core. Each observation peels back another layer, revealing more of the hidden heartbeat at the galaxy's centre. For most of human history, the galactic centre was invisible, a mystery hidden behind dark lanes of dust. Only in the last century have we gained the means to see it indirectly. That hiddenness gives it a special quality, as if the galaxy keeps its heart veiled, allowing only glimpses through special instruments. And yet, we know it's there. The motions of stars confirm it, the energy bursts testify to it, and the models of galactic structure all point inward. The centre is real, powerful and constant, whether or not we see it directly. Thinking about the galactic centre can bring a sense of scale that is hard to absorb. We live tens of thousands of light years from it, circling quietly in the disk, yet our fate is tied to it. The Sun orbits because of the mass it holds. The spiral arms persist because of its influence. The history of star formation, the recycling of gas, the very existence of planets like Earth all traced back to processes centred there. It is not just a point in the sky, it is the axis on which our galactic life turns. And while we can't see it with our eyes, we can still connect to it. On a clear night, look toward the southern sky where Sagittarius rises. Imagine beyond the dust and glow, past the crowded star fields, into the hidden core. There lies the black hole, the clusters, the churning clouds, all condensed into a space that defines us on the larger scales. You may not see the heartbeat, but you are living in rhythm with it. Every orbit, every rotation, every moment tied to its gravity. When astronomers first suspected there might be something extraordinary at the very centre of the Milky Way, the idea seemed almost too strange to be real. The notion of a black hole, an object so dense that not even light could escape its gravity, sounded like something out of speculation rather than science. Yet over decades of patient observation, the evidence has grown so compelling that it now stands as one of the most remarkable discoveries in modern astronomy. At the heart of our galaxy lies a supermassive black hole known as Sagittarius A, an invisible anchor with a mass equivalent to about 4 million suns. What does it mean to say that there is a black hole at the centre? It means that billions of stars, clouds of gas, and entire spiral arms orbit around an unseen concentration of gravity. We cannot look directly at the black hole in visible light, because by definition it emits nothing. The boundary around it, called the event horizon, is the point where escape becomes impossible. Any light that crosses that boundary is lost forever, trapped by gravity. Yet we can trace its presence by watching how nearby stars move. Their orbits whip around an invisible point, some completing circuits in just a few years. Only a black hole of immense mass could explain such motions. The discovery of Sagittarius A came not from a single observation but from years of effort. Teams of astronomers in Europe and the United States tracked the positions of stars near the galactic centre with increasingly precise instruments. Using infrared telescopes that could peer through the obscuring dust, they followed stars curving in tight ellipses. One in particular, known as S2, completed a full orbit in just 16 years, coming within a hair's breadth, in cosmic terms, of the black hole. By measuring its speed and trajectory, scientists could calculate the mass of the object it orbited. The result was unmistakable: millions of solar masses compressed into a space smaller than our solar system. In 2020, the Nobel Prize in Physics was awarded to Reinhard Genzel and Andrea Ghez for their pioneering work in revealing this black hole through stellar orbits. Their decades of persistence confirmed what theory had long predicted. Then, in 2022, the Event Horizon Telescope collaboration released the first direct image of Sagittarius A. Using a network of radio telescopes spanning the globe, the team synthesized an instrument the size of Earth itself. The result was a blurry ring of glowing gas, distorted by extreme gravity, surrounding a dark shadow. That shadow was the event horizon of the Milky Way's black hole. For the first time, humanity had captured a glimpse of the very edge of nothingness in our own galaxy. Despite its immense mass, Sagittarius A is quiet by cosmic standards. Many other galaxies host black holes that blaze with radiation, feeding on torrents of gas and shining as quasars visible across billions of light years. By comparison, our central black hole is starved. Only small amounts of matter fall into it, producing occasional flares of X-rays or radio bursts. For Earth, this is a blessing. An active quasar at the core would flood the galaxy with high-energy radiation, making conditions far less hospitable for life. Instead, Sagittarius A hums softly, a dormant giant biding its time. But what exactly happens near a black hole? The environment around Sagittarius A is shaped by an accretion disk of hot gas spiralling inward. As the gas approaches the event horizon, friction and compression heat it to millions of degrees, causing it to emit X-rays and radio waves. These signals are what the Event Horizon Telescope detects, not the black hole itself, but the glowing material on the brink of disappearance. Occasionally magnetic fields twist and snap near the disk, producing brief but intense outbursts. Astronomers have watched Sagittarius A flare unpredictably, brightening for hours before fading back to quiet. To understand how strange a black hole is, imagine compressing the sun into a sphere just a few kilometres across. That is the scale of density involved. In the case of Sagittarius A, 4 million suns are crushed into a region smaller than the orbit of Mercury. The escape velocity at its surface exceeds the speed of light, which is why nothing can escape. Space and time themselves are bent inward, warped to such an extent that our usual concepts of distance and duration break down. The equations of general relativity describe it, but the human mind struggles to visualize. It is less like an object and more like a hole in the fabric of reality, a place where the rules we know give way to extremes. For decades, black holes were treated as theoretical curiosities. Einstein's equations predicted them, but even he doubted they could exist physically. It took the discovery of X-ray binaries, where a visible star orbited an unseen massive companion, to convince astronomers that stellar mass black holes were real. Then came evidence of supermassive ones, lurking at the centres of galaxies. Now we know that nearly every large galaxy has one, their masses scaling with the size of their hosts. In some way, not yet fully understood, galaxies and black holes grow together, their fates intertwined. The presence of Sagittarius A is not an oddity. It is a defining feature of what it means to be a galaxy. The idea that the entire Milky Way revolves around a black hole may sound unsettling, but in reality, its influence at our distance is gentle. The Sun orbits not just Sagittarius A, but the combined mass of billions of stars and dark matter spread across the disk. The black hole dominates the central few light years, but beyond that, it is only part of the overall gravity well. If the black hole vanished magically tomorrow, the galaxy would hardly notice. Stars would continue orbiting the distributed mass. Its role is profound at the core, but on the scale of the galaxy, it is one actor among many. Yet its presence carries symbolic weight. A black hole at the heart of our galaxy is both literal and metaphorical, a dark anchor around which everything else turns. It reminds us that the cosmos contains extremes beyond our everyday comprehension. It is not just stars and planets, not just nebulae and clusters, but also these silent voids where matter disappears. The fact that we live in a galaxy with such a core connects us to the broader universe, where black holes are common, shaping the evolution of galaxies across billions of years. The science of Sagittarius A is still unfolding. Astronomers continue to refine measurements of its spin, its feeding habits, its interactions with nearby stars. One mystery is why it is so faint compared to theoretical expectations. Perhaps winds from nearby stars blow material away before it can fall in. Perhaps magnetic fields channel gas outward. Understanding this quietness could reveal new insights into black hole physics. Another area of study is the population of smaller black holes near the core. Dozens or even thousands may orbit in the crowded region, remnants of massive stars slowly spiralling inward over eons. Their interactions could generate bursts of gravitational waves detectable by future observatories. Even beyond science, the image of a black hole at the centre resonates deeply. Cultures throughout history have imagined cosmic hearts, sacred fires, or divine centres. Now we know that in our galaxy, the centre is occupied by something invisible, something that cannot be seen but can be felt. A place where time slows, where light itself cannot escape, where the known universe gives way to the unknown. For all our technology and equations, there remains mystery at the core. And perhaps that mystery is part of its power, drawing our curiosity as much as its gravity draws stars. On quiet nights, when you look towards Sagittarius, you can reflect on the fact that beyond the glowing star fields, beyond the clouds of dust, lies this hidden giant. Its heartbeat is not audible, its presence not visible, but the galaxy moves in rhythm with it. Every orbit of the sun, every passage of the spiral arms, every history of star formation is in some way tied to the existence of this black hole. It is both silent and central, absent to the eye but essential to the whole. And while we may never visit it, never send a probe across those thousands of light years to peer into its horizon, we can still connect to it through thought. The knowledge that such a place exists, that we live in a galaxy defined by it, can shift perspective. It can remind us how vast the universe is, how strange its contents are, and how much remains to be discovered. The black hole at the core is not just an object for scientists. It is part of the story of where we live, part of the background to our lives, part of the greater context of being. When most people imagine a galaxy, the first thought that comes to mind is stars, billions upon billions of glowing points, scattered across the spiral arms, making up the dazzling river of light in the sky. But the Milky Way is not just stars. Between them lies an enormous amount of material that never shines on its own, at least not in the way a star does. The galaxy is filled with clouds of gas, tiny particles of dust, and faint glows that give texture to the spaces between suns. These hidden components are easy to overlook when we picture the cosmos as a scattering of stars in blackness. Yet without them, the Milky Way would be unrecognisable, and life itself could never have arisen. The gas that fills the galaxy is mostly hydrogen, the simplest and most abundant element in the universe. It floats between the stars in vast clouds, sometimes spread thinly across hundreds of light years, sometimes packed densely in giant molecular complexes. Helium comes second, with trace amounts of heavier elements forged in earlier generations of stars. These clouds are the raw material from which new stars form. Over time, gravity pulls pockets of gas together, collapsing them into hot, dense cores that ignite nuclear fusion. The galaxy is, in a sense, recycling itself continuously, turning clouds of gas into new stellar generations, which eventually return material back into space through winds and supernovae. Dust, though less abundant, plays an equally important role. The word dust might suggest something ordinary, the kind you wipe off a shelf, but cosmic dust is different. These are tiny solid particles smaller than a micrometer, composed of carbon, silicates and metals like iron or nickel. They are forged in the atmospheres of dying stars and scattered into space when those stars shed their outer layers or explode. Dust grains float through the interstellar medium, absorbing and scattering light. To our eyes, they appear as dark lanes across the Milky Way, blotting out regions of stars. If you've ever noticed patches where the glowing band of the galaxy looks streaked or broken, you've seen dust at work. Far from being an annoyance, this dust is essential. It shields fragile molecules from ultraviolet radiation, allowing complex chemistry to take place inside clouds. It provides surfaces where atoms can stick and form new compounds. Without dust, the birth of stars and planets would be very different, perhaps even impossible. Our own solar system, including Earth itself, was built from material enriched with dust from ancient stars. The iron in your blood, the calcium in your bones, the silicon in your electronics, all of it once passed through the cycle of starlight and dust. Gas and dust together create a variety of glowing phenomena. When young stars form, their intense radiation ionizes the surrounding hydrogen, causing it to glow in vivid red and pink hues. These regions are called emission nebulae. The Orion Nebula, visible even without a telescope, is one such region, a cradle of new suns wrapped in gas. Reflection. Nebulae, by contrast, shine with a bluish light because dust grains scatter the starlight, much like Earth's atmosphere makes the sky blue. Then there are dark nebulae, clouds so thick with dust that they obscure all light behind them, appearing as voids against the starry background. To the eye, they are patches of mystery, but inside they may be brimming with new stars waiting to ignite. Radio and infrared telescopes have revealed even more hidden structures. Giant molecular clouds, some spanning hundreds of light years, drift through the spiral arms. They're cold by astronomical standards, only a few dozen degrees above absolute zero but rich in potential. Within them, molecules like carbon monoxide, ammonia, and even organic compounds have been detected. These clouds are the chemical laboratories of the galaxy, where the ingredients for planets and life are assembled. Observing them in radio wavelengths allows astronomers to trace their shapes and motions, even when they are invisible in visible light. The glow between the stars is not uniform. Some regions are quiet and sparse, with only faint traces of gas. Others are crowded with nebulae, clusters, and filaments of glowing material. Supernova explosions blast shock waves through the interstellar medium, compressing nearby clouds and triggering further star formation. Stellar winds carve out bubbles, creating cavities filled with hot plasma. The result is a patchwork of structures, constantly shifting over millions of years. If you could watch the galaxy and fast forward, you would see clouds colliding, collapsing, and dispersing in a slow, cosmic dance. Closer to home, our Sun also influences the local interstellar medium. Surrounding the solar system is a region known as the heliosphere, a bubble carved out by the solar wind. Beyond that bubble lies the interstellar gas of our neighbourhood, sometimes called the local interstellar cloud. The Sun and its planets are currently passing through this cloud, moving at tens of kilometres per second relative to the surrounding gas. It's a reminder that we are not drifting in empty space, but swimming through a medium filled with particles, however tenuous they may seem. The interplay of dust and gas also shapes how we see the galaxy. Much of the far side of the Milky Way is hidden from us by intervening clouds. For centuries, this made it difficult to know the galaxy's structure. Only by observing in radio and infrared, which can penetrate dust, did astronomers piece together the spiral arms and central bar. In a sense, we see only part of our galaxy directly. The rest must be reconstructed through clever use of other wavelengths. That limitation is part of the mystery, reminding us that our perspective is always partial. Despite their invisibility to the naked eye, dust and gas account for about 10 to 15% of the luminous matter in the Milky Way. That may not sound like much, but given the galaxy's size, it amounts to tens of billions of solar masses, enough to build countless new generations of stars, enough to ensure that the cycle of creation continues for billions of years to come. Without this reservoir, the galaxy would be stagnant, its stellar population aging and fading with no renewal. With it, the Milky Way is alive, always in the process of making and remaking itself. Dust also creates beauty in subtle ways. The reddish glow of distant stars is often caused by dust scattering shorter wavelengths, leaving longer ones to pass through. This effect, called interstellar reddening, shifts the colours we see. Photographs of the Milky Way often reveal intricate patterns of dark filaments, twisted and sculpted by magnetic fields and turbulence. These patterns are not random. They are the fingerprints of the galaxy's hidden forces, shaping how gas flows and stars are born. Looking at such images, you realise the Milky Way is not just a collection of points, but a living texture, rich with detail at every scale. Perhaps most humbling is the realisation that everything we are comes from this cycle. The carbon in our cells was once part of interstellar gas, fused in stars, scattered by explosions, and then gathered again. The oxygen we breathe was forged in ancient suns and released into the galaxy by dying giants. Even the gold in jewellery or electronics was created in cataclysmic events like neutron star collisions. The dust and gas between the stars are not just background, they are the source of everything tangible. To look at a nebula or dark cloud is to look at the material that eventually becomes life. Astronomers continue to study these components with increasing precision. Space observatories like Herschel and Spitzer have mapped dust emission in infrared, revealing cold clouds invisible in other light. The James Webb Space Telescope has recently captured stunning images of star-forming regions, showing pillars of gas and dust in exquisite detail. Each observation deepens our understanding of how the galaxy works, how it recycles matter, and how it sustains its grand cycle of birth and death. Yet even without these images, the concept alone, that between the stars lies a hidden richness, is enough to expand the imagination. It is tempting to think of the galaxy as mostly empty space, but in truth, no region is entirely empty. Even in the most rarefied stretches, there are still particles drifting, perhaps only a few per cubic centimetre, but present nonetheless. Over vast distances, even these sparse particles matter. They carry energy, magnetic fields, and influence the motions of stars and cosmic rays. The galaxy is a connected web, with dust and gas as its unseen threads. So when you look up at the Milky Way and notice the pale band crossing the sky, remember that what you are seeing is only part of the story. Hidden within are clouds and filaments, glowing and dark, forming and dispersing. The light of the stars is shaped by what lies between them, altered and filtered by dust and gas. The galaxy is not a static canvas, but a layered, evolving system. Every star you see, every shadowy lane you notice, is part of that ongoing cycle. And in that cycle, you too have a place. The atoms in your body, the water in your glass, the ground beneath your feet, all were once dust and gas drifting between the stars. You are living evidence of the galaxy's hidden processes. To understand dust and gas is to understand your own origins. The glow between the stars is not distant and irrelevant. It is intimate, woven into your very being, linking you to the Milky Way in the most literal sense. When people first began to wonder about the size of the Milky Way, the problem must have felt impossible. How do you measure something you cannot step outside of? It's one thing to measure a tree or a mountain, even a continent. You can walk around it, climb it, map it, and compare your measurements. But when you live inside the very thing you are trying to understand, you have no simple vantage point. The galaxy surrounds us on all sides, so large that no single glance can capture its shape. For centuries it was a question without an answer, a riddle that seemed destined to remain unsolved. And yet, patient observation, clever techniques, and a willingness to think beyond ordinary scales have slowly given us ways to measure the unmeasurable. Early astronomers tried to count stars in different directions to estimate the Milky Way's size. In the late 1700s, William Herschel conducted systematic star counts, pointing his telescope in various parts of the sky and recording how many stars he could see. His reasoning was simple. If more stars appeared in a given direction, that must mean the galaxy stretched farther that way. Fewer stars would mean a shorter extent. His results suggested that the galaxy was shaped like a flattened disk, with the sun near the centre. Although limited by the technology of his time and by the obscuring effects of dust, Herschel's work was one of the first attempts to turn the infinite-seeming sky into something measurable. Later, the invention of photography and spectroscopy opened new windows. Photographic plates could capture faint stars invisible to the human eye, extending the range of observations. Spectroscopy allowed astronomers to analyse the light of stars, measuring their temperatures, compositions, and motions. These tools revealed that many stars were far beyond what earlier telescopes had hinted. The scale of the galaxy kept expanding, and with it, our understanding of its immensity. One of the breakthroughs came in the early 20th century when Henrietta Leavitt, working at the Harvard College Observatory, discovered a crucial relationship in certain stars known as Cepheid variables. These stars pulsate regularly, brightening and dimming over fixed periods. Leavitt found that the period of a Cepheid's pulsation was directly related to its intrinsic brightness. By comparing how bright such a star appears from Earth to how bright it should be, astronomers could calculate its distance. This discovery transformed astronomy, providing a reliable yardstick for measuring vast distances. It allowed scientists to chart the structure of the Milky Way with new accuracy, and later to prove that galaxies beyond our own existed. Still, even with better tools, the problem of measuring the galaxy's size remained daunting. Light from distant stars was dimmed and reddened by interstellar dust, making them harder to detect. The disk's sheer scale meant that even the most luminous objects could fade below detectability before reaching us. Astronomers needed other methods, and they found them in radio astronomy. Hydrogen, the most abundant element in the galaxy, emits radio waves at a wavelength of 21 centimetres. Unlike visible light, these waves can pass through dust clouds. By mapping the 21 centimetre emissions across the sky and using the Doppler effect to measure their motions, astronomers traced the spiral structure of the Milky Way. Suddenly, the invisible became visible, and the galaxy's arms took shape on our maps. In recent decades, technology has advanced even further. The Gaia spacecraft, launched by the European Space Agency, is currently measuring the positions and motions of more than 1 billion stars with unprecedented precision. By triangulating their positions through parallax, the slight shift in apparent location as Earth orbits the Sun, Gaia provides direct distances to stars thousands of light-years away. The result is the most detailed three-dimensional map of the Milky Way ever created. Every update refines our knowledge, showing the true shape of the arms, the tilt of the disk, and the clustering of stars in exquisite detail. Yet even with these tools, the question, how big is the galaxy, resists a single answer. It depends on what you include. If you measure only the disk where most stars lie, the diameter is about 100,000 light-years. If you include the sparse halo of stars and globular clusters, the span grows to several 100,000 light-years. If you account for the dark matter that outweighs the visible matter, the full gravitational influence of the Milky Way may extend nearly 1 million light-years. Each definition gives a different size, all of them correct in their own way. Measuring the galaxy is not about finding one number, but about understanding layers of structure. The units themselves are difficult to imagine. A light-year is nearly 10 trillion kilometres. When we say the galaxy is 100,000 light-years across, we are speaking of distances so large that ordinary metaphors collapse. Even the fastest spacecraft humanity has ever built would take millions of years to cross such a span. Astronomers often rely on scaling analogies. If the Milky Way were reduced to the size of North America, the solar system would fit inside a coffee cup. If the galaxy were a dinner plate, the distance between the Sun and Pluto would be thinner than a hair. These comparisons are imperfect, but they give a glimpse of just how unmeasurable the unmeasurable feels. Another approach is to measure the galaxy's mass rather than its size. By tracking the motions of stars and gas, astronomers calculate the total gravitational pull. The result is astonishing. The Milky Way contains the equivalent of 1 to 2 trillion solar masses, yet most of that mass is invisible in the form of dark matter. The stars we see, the nebulae we photograph, the dust we detect, all of that accounts for only a small fraction. Measuring the unmeasurable means grappling with something we cannot see directly, something whose presence is revealed only through its pull on what we can see. Globular clusters, dense spheres of ancient stars orbiting the Milky Way, provide another yardstick. Their positions and motions trace the outer halo, marking the edges of the galaxy's influence. By studying these clusters, astronomers estimate how far the Milky Way extends and how much mass it contains. Each cluster is like a lantern in the dark, shining from the outskirts, helping define the boundaries of our galactic home. Despite all these tools, uncertainty remains. Measurements differ by tens of thousands of light-years, depending on methods and definitions. The galaxy is not a neatly bounded object, but a diffuse, evolving system. Stars drift outward. Satellites merge inward. Streams of gas weave across intergalactic space. The edges blur. To measure the Milky Way is to measure something in motion, a target that shifts as we study it. It is both a scientific challenge and a philosophical reminder that some things resist precise boundaries. Even so, the progress is remarkable. From Herschel's simple star counts to Gaia's billion-star catalogue, humanity has stretched its reach across unimaginable scales. Each step forward reveals more detail, more structure, more subtlety. We are measuring the unmeasurable not by reducing it to simplicity, but by embracing its complexity. The galaxy is not a single number, but a tapestry of dimensions: diameter, thickness, mass, luminosity, and age. Together they form a picture that is always incomplete but always improving. There is also a personal dimension to all this measuring. Every number we assign, every map we draw, helps us situate ourselves in the cosmos. To know the galaxy is 100,000 light-years across is to know that our lives occupy a tiny corner of something vast. To know it contains 1 trillion solar masses is to understand that our planet is a speck in an immense gravitational system. The act of measuring, even imperfectly, grounds us in reality. It transforms awe into knowledge without diminishing wonder. And yet, for all the progress, the galaxy retains its mystery. The farther out we look, the harder it becomes to define. The halo stretches thinly into intergalactic space, merging almost imperceptibly with the domain of neighbouring galaxies. The line between Milky Way and not Milky Way is not clear. Measuring the unmeasurable means accepting ambiguity. It means recognising that boundaries are sometimes human constructs, imposed on a universe that does not obey our neat divisions. Still, the attempt matters. Each new survey, each refinement, brings the unmeasurable a little closer to comprehension. Not complete comprehension, perhaps never that, but enough to weave a coherent story. Enough to know where we are, how we fit, and what surrounds us. The galaxy's size may be staggering, but it is also knowable in degrees, measurable in steps, approachable through patient effort. The unmeasurable becomes measurable not by shrinking it, but by expanding ourselves. And so, when you think about the Milky Way's size, you might picture astronomers hunched over telescopes, watching stars drift across detectors, or satellites scanning the sky with unblinking eyes. You might imagine computer models crunching through data, fitting spiral patterns and halos. Each act of measurement is a thread, and together they weave a picture of something too large to see at once. That picture is still incomplete, but it is growing, and in it we find ourselves living inside a galaxy that is at once unmeasurable and measured, unknowable and known. When you start talking about the scale of the galaxy, the usual units we use in everyday life quickly fall apart. Kilometres and miles, useful for measuring roads or flights, become absurd when stretched to cosmic distances. Even astronomical units, the span from Earth to the Sun, begin to lose their utility after only a few steps beyond the solar system. What astronomers needed was a ruler that matched the vastness of space, a way to describe separations so immense that ordinary numbers would otherwise become unwieldy. That ruler is the light year, the distance light travels in a single year. It may sound like a measure of time, but it is truly a measure of distance, and it has become the gentle tool by which we navigate the universe. Light is the fastest thing known, moving at about 300,000 kilometers per second. In the time it takes to blink, a beam of light could circle Earth more than 7 times. Stretch that speed across a year, and the distance covered is nearly 10 trillion kilometers. That is 1 light year. Already it's almost beyond imagining. A car driving at highway speed would take more than 10 million years to travel just 1 light year. Even a spacecraft like Voyager 1, which has been racing away from Earth for decades, has covered only a tiny fraction of that distance. And yet, when we speak of galaxies, we casually describe spans of tens, hundreds, or thousands of light years as if they were ordinary numbers. The beauty of the light year is that it converts unimaginable distances into manageable figures. When we say the nearest star system, Alpha Centauri, is 4.3 light years away, the number is still large but not absurd. We can picture it as 4 steps on the ruler of light years. When we say the disk of the Milky Way is 100,000 light years across, we're speaking in units that fit the scale, even if the reality remains staggering. It's a gentle ruler not because the numbers are small, but because they are usable, giving us a language to describe the otherwise indescribable. There's also a poetic truth hidden in the concept. Because light takes time to travel, when we measure in light years, we are also measuring in years of history. To say something is 10,000 light years away is to say we're seeing it as it was 10,000 years ago. Distance and time merge in the same phrase. The Milky Way is not just wide in space, it is deep in time. Every star we see is also a message from the past, its light crossing the gulf to reach us only after lifetimes of travel. The light-year ruler measures both the vastness of space and the memory of time carried within it. The need for such a measure arose naturally as astronomy grew more precise. Early observers could chart positions and motions, but distances were elusive. Without knowing how far away stars were, the scale of the universe was guesswork. The method of parallax, measuring the apparent shift of a star against background stars as Earth moves around the Sun, was the first reliable way to establish stellar distances. The angles are tiny, often less than a fraction of a second of arc, but with careful instruments they reveal distances in light years. The nearest stars show detectable shifts. Farther ones require indirect methods, like Cepheid variables or standard candles, to step the scale outward. The light year became the natural language to describe these results. Even today, astronomers often switch between light years and parsecs, another unit based on parallax. 1 parsec is about 3.26 light years. Professionals may favour parsecs, but the light year remains the more intuitive measure for most people. It connects directly to the concept of light speed, something even non-scientists can appreciate. You can say, this star is 10 years of light travel away, and the meaning becomes tangible, even if the number is vast. It links distance to time in a way no other unit does. Within the Milky Way, light years define the scale of every structure. The distance to the nearest stars is a few light years. The width of spiral arms is thousands. The full disk stretches across 100,000. The halo extends hundreds of thousands. When astronomers describe the galaxy's thickness, they say the thin disk is about 1,000 light years deep. These numbers become coherent when expressed in light years. They allow us to compare, to situate, to imagine. Without the light year, the galaxy's size would be buried in strings of zeros, incomprehensible and alienating. With it, we can speak plainly, even calmly, about distances that defy daily experience. And yet, for all its usefulness, the light year also humbles us. Knowing that even the nearest stars are years away at the fastest possible speed underscores our isolation. Messages we might send to hypothetical neighbours would take decades to arrive. Journeys to even the closest systems are beyond our current capabilities. The light year ruler tells us not only how large the galaxy is, but how far our reach still falls short. It is a gentle ruler, but also a stern one, reminding us of limits we cannot yet overcome. Still, there is comfort in the constancy. Light speed is a universal constant, the same everywhere, unaffected by the motion of source or observer. That makes the light year a dependable unit, one we can trust across all of space. It doesn't matter where in the galaxy you are, how fast you move, or what conditions surround you. The distance light travels in a year is the same. In a universe full of complexity, that reliability is a gift. It lets us measure, compare, and communicate across unimaginable expanses. The light year also reveals something subtle about our place in the cosmos. When we look out at the galaxy, we are not seeing it as it is now, but as it was across a spread of times. Stars 1,000 light years away are shown to us as they were a millennium ago. The galactic centre, 26,000 light years away, is seen as it was when humanity had only just begun making tools. The far side of the galaxy, 100,000 light years distant, shows us a view that predates our species entirely. In this sense, the Milky Way is a time machine as much as a space. The light year ruler measures not just where things are, but when we are seeing them. Astronomers use light years not just for distances, but for scales of energy and movement. Supernovae are described in terms of their light echoes, ripples of illumination moving outward across light years. Star clusters are measured by their spread in light years. Even cosmic events like gamma-ray bursts are studied by how their light travels across light years to reach us. The unit has become more than a convenience. It is woven into the very language of astronomy, the default way we describe the structure of the universe. For the Milky Way, light years provide a map of our home. The Sun is one of billions, orbiting at about 26,000 light years from the centre. The nearest spiral arm is thousands of light years across. The farthest globular clusters orbit at hundreds of thousands. To speak these numbers in light years is to make them digestible, to bring the galaxy into mental reach. We may never travel such distances physically, but we can travel them with thought, stepping across light year by light year, imagining our place within the vastness. And yet, for all its practicality, the light year remains something abstract until you reflect on what it means. Imagine a beam of light leaving a star, photons streaming outward in every direction. Some of those photons travel unhindered for years, decades, millennia. Eventually a few strike the back of your eye as you look at the night sky. In that moment you're catching the end of a journey measured in light years. The ruler is not just a tool of science, it is an intimate connection. Each star you see is a message delivered by light years of travel, arriving precisely in your moment of observation. The phrase, gentle ruler, fits because it allows us to handle immensities without being crushed by them. The galaxy could be described in kilometres, but the numbers would be so enormous that they would lose meaning. The light year takes those impossibilities and scales them into something the human mind can at least begin to grasp. It invites us to measure without despair, to explore without being overwhelmed. It is a unit that bridges the gap between our small lives and the vastness around us, offering a way to speak calmly about the incomprehensible. So when you hear that the Milky Way is 100,000 light years across, don't rush past the number, let it linger. Imagine light itself, the fastest thing in the universe, racing for a century just to cover 100 light years, then repeating that journey 1,000 times more to span the disk. Imagine those beams crossing dust clouds, weaving between stars, carrying their silent record of the galaxy's shape. Each light year is both distance and story, both ruler and memory, and together they measure not just the galaxy's size but our place within its rhythm. When you look up at the sky on a clear night, the Milky Way appears as a hazy band of light, stretching from one horizon to the other. From that perspective alone, it might be tempting to think of it as a flat streak, a straight path through the heavens, but the true shape of our galaxy is far more complex, and discovering it has been one of astronomy's most challenging tasks. Unlike with other galaxies, which we can observe from the outside, we are trapped inside the Milky Way itself. It is like trying to describe the outline of a vast forest while standing among the trees. We see only what surrounds us, not the whole. Yet over time, with patience and creativity, astronomers have pieced together a portrait of the Milky Way's true shape. The first clue that our galaxy was disc-shaped came from the simple observation that the band of stars forming the Milky Way stretches in a narrow line across the sky, rather than being evenly distributed. That band reflects the plane of the galactic disk, where most of the stars, gas and dust are concentrated. When William Herschel attempted to map the distribution of stars in the 18th century, he proposed a flattened disc-like structure. His methods were limited, but he was correct in the broad strokes. The Milky Way is a vast disk, tens of thousands of light years across, and only about 1,000 light years thick in the region where most stars reside. As telescopes improved, more detail emerged. Observations in radio and infrared, which can see through dust clouds, revealed the spiral arms that wind around the disk. The Milky Way is not just a featureless plate, but a barred spiral galaxy, with a central bar-shaped concentration of stars extending across the bulge. From this bar, arms of stars and gas curve outward, wrapping around the galaxy in a graceful pattern. Our own solar system is located in one of the smaller arms, a spur between two major ones, some 26,000 light-years from the centre. The bulge at the galaxy's heart is another important feature. It is a dense spheroidal concentration of older stars surrounding the supermassive black hole at the centre. The bulge is not perfectly round, but somewhat elongated, blending into the central bar. This region is crowded with stars, clusters, and gas, forming a stark contrast to the relatively calm neighbourhood where the Sun resides. From Earth, the bulge is visible as the thickening of the Milky Way's band in the direction of Sagittarius, where the light of countless stars overlaps into a bright glow. Beyond the disk and bulge lies the halo, an extended, roughly spherical region filled with sparse stars, globular clusters, and dark matter. The halo stretches far beyond the visible disk, hundreds of thousands of light-years in every direction. It is faint and difficult to observe, but it is crucial to the galaxy's structure. The halo contains some of the oldest stars in the Milky Way, relics from its early formation, as well as the invisible mass of dark matter that provides much of the galaxy's gravitational pull. Without the halo, the spiral arms would not hold together. The galaxy would fly apart. One surprising discovery in recent years is that the Milky Way's disk is not perfectly flat. Instead, it is warped and twisted, like a vinyl record left in the sun. The outer regions bend up and down, forming a gentle S shape. This warp may be caused by the gravitational influence of satellite galaxies, like the Magellanic Clouds, or by the uneven distribution of dark matter. Whatever its cause, it shows that the Milky Way is not a rigid structure, but a living, dynamic one, shaped by its interactions with the surrounding universe. Another detail is the presence of streams and remnants of smaller galaxies that have merged with the Milky Way. As our galaxy has grown over billions of years, it has consumed countless dwarfs, tearing them apart and incorporating their stars. These tidal streams arc across the halo, faint trails of stars that trace the paths of past collisions. The Sagittarius dwarf galaxy, for instance, is currently being disrupted, its stars stretched into a long ribbon wrapping around the Milky Way. These features blur the edges of the galaxy, making its true shape not a clean outline, but a layered history of mergers. The Milky Way's shape is also revealed by studying the motions of stars. By measuring how fast stars orbit at different distances from the centre, astronomers construct what is known as a rotation curve. Instead of declining at the edges, as one might expect if only visible matter were present, the rotation speed remains flat. This is one of the key pieces of evidence for dark matter, an invisible substance that surrounds the galaxy and shapes its form. Without it, the spiral arms would unravel. With it, the galaxy holds together in a vast, unseen embrace. Comparisons with other galaxies provide further clues. When we look at spirals like Andromeda or the Whirlpool galaxy, we see familiar patterns: central bulges, winding arms, extended halos. The Milky Way resembles these, though each galaxy has its quirks. By studying them, we refine our picture of our own. It is like looking at neighbouring houses to infer the shape of our own roof, hidden from view because we stand beneath it. For all the progress, uncertainty remains. The exact number of spiral arms is still debated. Some maps show 4 major arms, others suggest 2, with spurs and branches. The distances to far regions remain challenging to measure, and dust continues to obscure parts of the view. The Milky Way's true shape is not yet fully settled. It is a work in progress, a sketch that grows more detailed with each observation. The Gaia spacecraft has revolutionized this effort by mapping the positions and motions of over 1 billion stars. With its data, astronomers can see the subtle ripples in the disk, the waves of motion caused by past collisions, the arcs of stars in the halo. These details add depth to the portrait, showing the Milky Way not as a static object, but as a galaxy with scars, rhythms, and growth. The true shape is not a snapshot, but a story, unfolding across billions of years. And yet, for all the complexity, one thing is clear: the Milky Way is immense. From the dense bulge at its core to the faint reaches of its halo, it stretches across hundreds of thousands of light years. Its spiral arms curve gracefully, its bar channels stars inward, its halo extends outward into intergalactic space. It is not a simple band of stars, but a layered dynamic system. To live within it is to inhabit something vast beyond easy comprehension, a structure so large that we see only fragments at a time. The true shape of the Milky Way is therefore both a scientific fact and a humbling reminder. Fact, because we can describe its disk, bulge, arms and halo with increasing accuracy. Reminder, because we cannot step outside to see it whole. Our perspective will always be limited, our maps always partial, and yet, through the patient accumulation of data, the unseeable becomes visible, the hidden shape takes form. It is a triumph of human curiosity, a way of reaching beyond our immediate senses to grasp the larger structure that holds us. So when you look up at the night sky and trace the glowing band overhead, you can imagine the broader form. Picture the disk, wide and thin, spiralling outward from a dense centre. Picture the bulge glowing with ancient stars, the bar stretching across, the arms curling away. Picture the halo, faint but immense, reaching far into the darkness. That is the Milky Way's true shape, not just the band you see but the vast system it represents. And though you will never see it from the outside, you live within it, part of its form, orbiting quietly as the galaxy turns. When most people think of the Milky Way, the focus naturally falls on the glowing band of stars, the spiral arms, the dense bulge in the centre, or the nebulae scattered across the disk. But the galaxy does not end where the glow fades from sight. Extending far beyond the bright disk is a vast, nearly invisible region known as the halo. This halo does not shine with the concentrated brilliance of the arms. Instead, it lingers as a ghostly realm, faint and elusive, populated by sparse stars, ancient clusters, and an overwhelming presence of dark matter. It is as much a part of the Milky Way as the arms themselves, and without it the galaxy would not hold together. The halo is difficult to study because it emits so little light. Unlike the disk, where billions of stars crowd together, the halo's stars are spread thinly across an enormous volume. Imagine walking into a forest where the trees suddenly grow miles apart. From your spot on the ground, it would almost feel empty, even though the forest still extends around you. That is the halo's nature. Vast, diffuse, yet significant. Its diameter may stretch hundreds of thousands of light years, perhaps even close to 1 million if you include its outermost influence. Within that sphere lies the faint scaffolding that defines the Milky Way's true extent. Among the halo's most striking features are the globular clusters. These are tightly packed spherical collections of stars, some containing hundreds of thousands or even millions of suns bound together by gravity. Unlike the open clusters scattered in the disk, globular clusters are ancient, with ages exceeding 10 billion years. They are relics of the galaxy's youth, survivors from a time when the Milky Way was still assembling itself. Orbiting high above the disk in long looping paths, they form a kind of shell around the galaxy, markers of its history. From Earth, some globular clusters are visible through small telescopes appearing as fuzzy balls of light. Through larger instruments, they resolve into glittering swarms, breathtaking in their density. Each cluster is like a fossil in the halo, carrying the memory of the galaxy's earliest epochs. But stars and clusters are only part of the halo. Surrounding the Milky Way is an enormous quantity of gas, stretching far beyond the visible disk. This gas is extremely thin, much more tenuous than the air we breathe, but because it fills such a huge volume, its total mass is substantial. Observations in ultraviolet and X-rays have revealed this hot, diffuse corona of gas, extending hundreds of thousands of light years. Some of it may be material left over from the galaxy's formation, While some may be accreted from intergalactic space, it is not uniform. Clouds drift through it, some traced by their absorption of quasar light shining from even farther away. These clouds are like ghosts in the halo, nearly invisible except when backlit by the cosmos. One of the most famous of these ghostly features is the Magellanic Stream, a long ribbon of gas stretching across the sky, torn from the small and large Magellanic Clouds, two dwarf galaxies orbiting the Milky Way. This stream arcs across hundreds of thousands of light years, weaving through the halo like a trail of vapour. It is evidence of the ongoing interaction between our galaxy and its satellites, showing that the halo is not a passive shell but an active environment shaped by gravity, collisions and flows of matter. Other stellar streams lace the halo as well. These are remnants of smaller galaxies that the Milky Way has devoured over time. As a dwarf galaxy is captured, tidal forces stretch it apart, scattering its stars into long arcs. These streams remain coherent for billions of years, like scars across the halo telling the story of mergers and growth. The Sagittarius stream, for example, is the shredded remains of the Sagittarius dwarf galaxy, currently being pulled into the Milky Way. By mapping these streams, astronomers reconstruct the galaxy's violent history, learning how the halo grew from countless smaller systems. Dark matter is the most mysterious component of the halo. Though invisible, it dominates the mass. The motions of stars and gas cannot be explained by visible matter alone. Only by invoking a vast halo of unseen material can the galaxy's rotation be understood. This dark matter halo likely extends far beyond the visible disk, enveloping the Milky Way in an invisible cocoon. Its nature remains unknown, whether exotic particles, new physics, or something else entirely, but its influence is undeniable. Without it, the spiral arms would not persist, and the galaxy would fly apart. In this sense, the true shape of the Milky Way is defined less by the stars we see, and more by the dark matter halo that binds them. Studying the halo requires creative techniques. Because its stars are so sparse, astronomers search for specific types of markers, RR Lyrae, variable stars, blue horizontal branch stars, or distant quasars shining through halo gas. By analysing how light is absorbed, scattered, or shifted, they infer the presence of otherwise invisible matter. Space telescopes like Hubble have been particularly valuable, using the ultraviolet signatures of halo gas to trace its extent. Each observation adds another piece to the puzzle, revealing the faint architecture that supports the galaxy. The halo also acts as a bridge between the Milky Way and the larger universe. It is the region where our galaxy exchanges material with intergalactic space, accreting fresh gas from cosmic filaments and shedding enriched gas through outflows driven by supernovae. This circulation sustains the galaxy, feeding future generations of stars while dispersing the products of old ones. Without the halo, the Milky Way would be a closed system, doomed to exhaust its gas. With it, the galaxy participates in the larger cosmic web, connected to structures far beyond itself. In a sense, the halo is the Milky Way's memory. Its globular clusters remember the earliest days, its streams record past mergers, its dark matter preserves the invisible framework of formation. Its gas connects the galaxy to the wider universe. Though it is faint and ghostly, it carries the deepest truths about what the Milky Way is and how it came to be. To study the halo is to study the history written in the margins of the galaxy, the traces left behind long after the main body has taken shape. From Earth, of course, none of this is obvious. The halo does not blaze across the sky. You cannot point to it with the naked eye. It reveals itself only through careful science, through subtle measurements and patient analysis. Yet once you know it is there, the way you imagine the galaxy changes. No longer just a bright disk, the Milky Way becomes a layered structure, luminous at its core but wrapped in vast invisible arms. The halo turns the galaxy from a thin band into a sprawling sphere, reaching out into the darkness with ghostly clouds. What makes the halo so compelling is that it stretches our imagination of what a galaxy is. The disk and arms are familiar, easily visualized, but the halo is harder to grasp, because it is defined as much by what we cannot see as by what we can. It forces us to accept that the Milky Way's boundaries are not sharp, that its form is not confined to the visible. It reminds us that the galaxy is not just what glitters in the night, but also what lurks in shadow, holding everything together. And within that shadowy realm, the galaxy continues to grow. Streams continue to fall in, gas continues to circulate, dark matter continues to shape the orbits of stars. The halo is not static, it is active, evolving, always changing. To imagine it is to picture the Milky Way breathing, expanding and contracting, consuming and releasing, tied to the larger currents of the cosmos. So when you think about the Milky Way, don't stop at the glowing arms or the bright core. Imagine also the faint, ghostly halo, filled with ancient clusters and invisible matter stretching far beyond the stars you see. Picture the streams weaving through it, the clouds drifting in silence, the dark matter shaping unseen paths. That is the Milky Way's full body, not just the glittering skin, but the hidden form. To know the halo is to glimpse the galaxy's soul, quiet, vast, and enduring. When you think of the Milky Way, it's natural to picture it as a single, enormous structure, complete in itself, spinning quietly through space. But the galaxy does not drift alone. All around it are smaller companions, dwarf galaxies that orbit the Milky Way in a complex gravitational dance. Some are close and visible, others faint and hard to detect, their stars spread thinly across the sky. Together they form a community, a system of satellites that remind us the galaxy is part of a larger neighbourhood. These companions may be small compared to the Milky Way, but they carry stories of their own, and their interactions shape our galaxy's past and future. The most famous of these companions are the large and small Magellanic Clouds, visible from the southern hemisphere as irregular smudges of light. To the naked eye, they appear as faint patches, not unlike detached pieces of the Milky Way itself. For centuries, sailors used them as markers in the night sky, naming them after the explorer Ferdinand Magellan, who described them during his circumnavigation of the globe. Today, we know that they are dwarf galaxies orbiting the Milky Way, each with billions of stars of its own. The Large Magellanic Cloud, or LMC, is the larger of the two, about 160,000 light-years away, while the Small Magellanic Cloud, or SMC, lies a little farther at about 200,000 light-years. Both are irregular in shape, distorted by their interactions with each other, and with the Milky Way's gravity. The Magellanic Clouds are not static satellites, they are in motion, orbiting and being tugged, shedding material as they go. Streams of gas trail behind them, most notably the Magellanic Stream, a ribbon of hydrogen stretching across half the sky. This stream is evidence of the gravitational tug-of-war between the dwarfs and the Milky Way, a reminder that galaxies are not rigid but fluid, constantly exchanging material. Within the Magellanic Clouds themselves, star formation is vigorous, fueled by the abundance of gas. The Tarantula Nebula in the LMC is one of the most active stellar nurseries known, a region where massive stars form in clusters, lighting up the surrounding gas with brilliant energy. Beyond the Magellanic Clouds, the Milky Way hosts dozens of smaller companions, many of them faint and hard to see. Some are so diffuse that their stars barely stand out against the background of the galaxy. These ultra-faint dwarfs contain only a few thousand stars, bound together by dark matter halos. They are like tiny lanterns flickering at the edge of the Milky Way's reach. In recent decades, surveys such as the Sloan Digital Sky Survey and Gaia have uncovered many of these hidden companions, revealing that the Milky Way's family is larger than once thought. Each discovery adds to the picture of a galaxy surrounded by a retinue of smaller siblings. These dwarf galaxies are not just passive ornaments, they play an active role in the Milky Way's growth, Over billions of years, the Milky Way has consumed many such companions, tearing them apart with tidal forces and absorbing their stars into its halo. The streams of stars arcing across the sky are remnants of these devoured dwarfs. The Sagittarius dwarf galaxy, for example, is currently in the process of being dismantled, its stars stretched into a long ribbon wrapping around the Milky Way. In this sense, the halo is not just a quiet shell, but a graveyard of past galaxies, each one leaving behind traces of its existence. The gravitational interactions between the Milky Way and its dwarfs are complex. As the smaller galaxies orbit, they perturb the disk, sending ripples through it. Some of the waves and warps observed in the Milky Way structure may be the result of these encounters. The LMC in particular is massive enough to influence the Milky Way's motion. Recent studies suggest that the Milky Way itself is being tugged by the LMC, shifting slightly as the two galaxies orbit their common centre of mass. This is a reminder that even giants can be moved by smaller partners if those partners are close enough and heavy enough. Dwarf galaxies are also valuable to astronomers because they offer laboratories for studying dark matter. Their motion suggests that dark matter dominates their mass, even more so than in larger galaxies. By observing how stars move within these dwarfs, scientists can probe the nature of the invisible substance shaping the cosmos. Each dwarf becomes a kind of natural experiment, providing clues to one of the greatest mysteries in astrophysics. What makes these dwarfs even more fascinating is their diversity. Some, like the Magellanic Clouds, are rich in gas and actively forming stars. Others are quiescent, their gas long since stripped away, leaving behind only old, faint stars. Some are irregular in shape, stretched by tidal interactions. Others are more spherical, like miniature versions of elliptical galaxies. Together they show that even at small scales, galaxies can take many forms, shaped by their histories and environments. For the Milky Way, these companions are both past and future. In the past, many have already merged, their stars now indistinguishable from the larger population. In the future, some of those that remain may be consumed. Over billions of years, the Milky Way will continue to grow by accreting its dwarfs, adding their stars and gas to its own. The process is slow on human timescales, but relentless on cosmic ones. It is part of the natural evolution of galaxies, a reminder that even giants are built from smaller pieces. The relationship between the Milky Way and its dwarfs also reflects the larger structure of the universe. Galaxies rarely exist in isolation. They form groups and clusters, bound together by gravity. The Milky Way and Andromeda are the two dominant members of the local group, but around them swarm dozens of smaller galaxies. The dwarfs orbiting the Milky Way are part of this group, a substructure within the larger whole. Their dance around us mirrors the dance of larger galaxies around each other, a fractal repetition of motion on different scales. From Earth, the presence of these dwarfs is subtle. Apart from the Magellanic Clouds, most are invisible without telescopes. Yet knowing they are there changes the way you imagine the night sky. The Milky Way is not alone, not a solitary island of stars, but the hub of a small system with companions circling quietly. Each of those companions holds its own stars, its own potential planets, perhaps even its own stories of life. To think of them is to expand the sense of home, to recognise that our galaxy is part of a family, not a lone wanderer. As telescopes grow more powerful, more dwarfs are being discovered. Some are so faint they were invisible until recently. Their stars spread so thinly that they blend with the background. Yet by analysing their motions, astronomers tease out their presence. Each discovery hints that there may be many more, hiding in the shadows, waiting to be found. The census of the Milky Way's companions is not yet complete. The dance continues and the partners are still being counted. These discoveries also provide insight into how galaxies form. In the early universe, small galaxies were common, merging over time to form larger ones. The Milky Way is the product of countless such mergers, and the dwarfs we see today are survivors of that earlier era. They are fossils of cosmic history, reminders of a time when galaxies were young and small. To study them is to look back billions of years, to glimpse the building blocks of cosmic structure. So when you think about the Milky Way, don't picture it in isolation. Imagine the Magellanic Clouds drifting nearby, their gas trailing into a long stream. Picture the faint dwarfs circling at great distances, their stars dim but real. Visualize the streams of stars that mark the remains of past companions. Together they form a dynamic system, a dance of giants and dwarfs, a story of growth through union and interaction. The Milky Way is not just a galaxy, it is the centre of a small community surrounded by partners, some vibrant, some fading, all moving together through the dark. If you stand outside on a clear night and look at the Milky Way stretched across the sky, it's easy to think of it as still, a quiet band of light hanging overhead. But in reality, the galaxy is anything but motionless. Every star you see is moving. Every cloud of gas, every cluster, every faint dwarf companion, all of it is orbiting around the centre. The Milky Way is spinning, an enormous whirlpool of stars, rotating with such precision that it has held together for billions of years. The scale of this rotation is staggering, and it leads to one of the great mysteries of modern astronomy: how the galaxy can spin so fast without flying apart. Our own sun is part of this great motion. Right now, as you sit listening, the solar system is orbiting the galactic centre at a speed of about 828,000 kilometres per hour. That sounds impossibly fast, but because the distances are so vast, it still takes the Sun about 225 million years to complete a single orbit. Since its birth 4.6 billion years ago, the Sun has circled the galaxy only about 20 times. During those circuits, continents on Earth have drifted, species have risen and fallen, and entire lineages of life have come and gone. Each galactic year is longer than the history of complex animals on our planet. When astronomers began to measure the motions of stars more carefully, they noticed something surprising. The stars far from the centre of the galaxy were orbiting just as quickly as those much closer in. According to the laws of gravity, stars on the outskirts should move more slowly, because they are farther from the mass concentrated at the centre. Planets around the Sun follow this pattern. Mercury moves fastest while Neptune creeps along slowly. But the galaxy does not behave like that. Its rotation curve is flat. Stars tens of thousands of light years from the centre circle, at almost the same speed as stars nearer in. This discovery was one of the first major clues to the existence of dark matter. If only the visible stars and gas were present, the outer parts of the galaxy would not have enough mass to keep stars moving so quickly. They would drift away, and the galaxy would unravel. The fact that they remain bound suggests there is much more mass than we can see. An invisible halo of dark matter surrounds the Milky Way, providing the extra gravity needed to hold everything together. Without it, the galaxy's spin would tear it apart. The concept of dark matter emerged in the 20th century, when astronomers like Vera Rubin measured galaxy rotation curves and found the same flat pattern everywhere they looked. It wasn't just the Milky Way. Other spiral galaxies showed the same mystery. The conclusion was unavoidable. Galaxies are filled with unseen mass, outweighing the visible stars by a factor of 5 or more. The precise nature of this dark matter remains unknown. It does not emit or absorb light. It interacts primarily through gravity, but its presence is essential to explaining why galaxies, including our own, remain intact as they spin. Even without dark matter, the dynamics of galactic rotation are fascinating. The stars and gas do not orbit as rigid parts of a solid wheel. Instead, they follow paths determined by the overall gravitational field. Stars closer to the centre do complete their orbits faster in terms of years, simply because their paths are shorter, but the speeds remain roughly consistent across the disk. This creates differential rotation, where the inner parts lap the outer parts over time. If the spiral arms were simply trails of stars, they would wind up and disappear. Instead, they are maintained by density waves, patterns that move through the disk, compressing gas and triggering star formation. From our vantage point, the motion is imperceptible. Constellations appear fixed, changing only over thousands of years. But on galactic timescales, everything is flowing. The sun drifts along its orbit, weaving gently above and below the galactic plane in a slow oscillation. Clusters move together, then disperse. Streams of stars arc across the halo, remnants of past mergers. Gas clouds swirl, collide, and collapse. The galaxy is alive with motion, every part orbiting in rhythm with the whole. To imagine the Milky Way's spin, picture a giant disk 100,000 light-years wide, filled with hundreds of billions of stars. Each star is a bead of light circling the centre. The entire structure rotates, not in a rigid spin but in a graceful flow. The bar at the centre channels stars and gas. The spiral arms curl outward. The halo envelopes it all. Gravity holds the dance together, a balance between centrifugal motion and inward pull. Without that balance, the galaxy would dissolve. With it, the galaxy endures for billions of years, stable yet dynamic. The stability of this rotation is one of the reasons galaxies can persist so long. Stars live out their lifetimes, gas recycles, new generations are born, and still the structure remains. Collisions with smaller galaxies create ripples, but the overall spin continues. It is a reminder of how robust gravity is. Even at such scales, it provides order, guiding motions that would otherwise scatter into chaos. The Milky Way spins not precariously but securely, its motion a natural consequence of its mass. Yet mysteries remain. The exact distribution of dark matter, the precise shape of the rotation curve, the influence of satellite galaxies, all of these are active areas of study. The Large Magellanic Cloud, for example, is massive enough that it may be tugging on the Milky Way's dark matter halo, distorting the motion of stars. Streams in the halo show evidence of past interactions that may have altered the rotation. Even the Sun's own orbit is not perfectly circular, but slightly elliptical, carrying it closer and farther from the centre and over time. The spin is steady, but it is also full of subtleties. Thinking about the galaxy's rotation can bring a sense of connection. Right now, you are moving with the Earth around the Sun at about 30 kilometers per second. At the same time, you and the Sun are moving around the galactic centre at more than 200 kilometers per second. Add to that the Milky Way's motion within the local group and the local group's motion through the larger cosmos, and you are part of a cascade of motions, all nested together. What feels like stillness is actually constant travel, a journey through space guided by gravity's hand. From Earth, we cannot see this motion directly, but we can measure it. Spectroscopy reveals the Doppler shifts of stars, showing how they move toward or away from us. Radio observations of hydrogen trace the rotation of the disk. Gaia's precise measurements of stellar positions and velocities provide a detailed map of the galaxy's dynamics. With each advance, the picture becomes clearer. A galaxy spinning gracefully, held together by both visible and invisible matter. Other galaxies confirm this pattern. When we look at spirals through telescopes, we see them rotating, their arms swirling around central bulges. The flatness of their rotation curves matches what we see in the Milky Way. The conclusion is universal. Galaxies spin without falling apart because of dark matter halos. The Milky Way is not unique in this respect, but a member of a cosmic family, all governed by the same hidden framework. And yet the knowledge that our galaxy spins so quickly and so steadily can be quietly comforting. It means we live in a structure that is stable on timescales far longer than human history. Whatever changes occur on Earth, the Milky Way's rotation continues. Stars orbit, arms wind, halos hold. We are part of that rhythm, carried along in a motion too vast to feel but too important to ignore. The galaxy spins, and we spin with it, orbiting quietly through the dark. When astronomers first tried to weigh the Milky Way, they naturally added up what they could see. The stars provided the most obvious contribution, billions of them scattered across the disk and bulge. Clouds of gas and dust added more, forming the raw material for future generations of stars. Globular clusters, star-forming regions, and glowing nebulae all contributed to the tally. But when the numbers were compared with how fast the galaxy rotates, something didn't add up. The visible matter was simply not enough to explain the motions. The outer stars were circling too quickly. The arms should have unravelled long ago. Something unseen was at work, an invisible mass holding everything together. That invisible mass came to be called dark matter. It is not dark in the sense of being black or shadowy, but dark in the sense of being undetectable by light. It does not shine, absorb, or reflect in any wavelength we know. Its presence is inferred entirely from gravity, from the way it bends the paths of stars, gas, and even light itself. In the Milky Way, as in countless other galaxies, dark matter outweighs visible matter by a large margin. For every kilogram of stars and gas, there are perhaps 5 kilograms of dark matter. Without it, the Milky Way could not exist as it does. The discovery of dark matter's influence was gradual. In the 1930s, the Swiss astronomer Fritz Zwicky noticed that galaxies in clusters were moving too quickly to be held together by visible matter alone. He proposed that missing mass must be present, an unseen component providing extra gravity. His idea was largely ignored at the time. Decades later, Vera Rubin and her collaborators measured the rotation curves of spiral galaxies and found the same discrepancy on smaller scales. Instead of declining speeds at the edges, the curves remained flat, as if galaxies were embedded in massive, invisible halos. Her careful work convinced the scientific community that dark matter was real, even if its nature remained mysterious. In the Milky Way, dark matter is thought to form a vast halo, spherical or slightly elongated, enveloping the disk and bulge. This halo extends far beyond the visible stars, perhaps hundreds of thousands of light years. Its density is highest near the centre, and decreases outward, but it never vanishes entirely. It shapes the orbits of stars in the disk, the paths of dwarf galaxies in the halo, and the motions of globular clusters. It is the unseen skeleton of the galaxy, giving structure and stability to what we can see. The idea of an invisible hand shaping the galaxy may sound strange, but evidence for it comes from many directions. Gravitational lensing, where light from distant objects is bent by intervening mass, reveals the presence of dark matter in both galaxies and clusters. Cosmic microwave background measurements show that dark matter was essential in seeding the growth of structure in the early universe. Computer simulations of galaxy formation only succeed when dark matter is included. The Milky Way is not unique in being influenced by this invisible component. It is universal, part of the very fabric of cosmic evolution. The exact nature of dark matter, however, remains unknown. One possibility is that it consists of undiscovered particles, beyond those in the standard model of physics. Candidates include WIMPs, weakly interacting massive particles, or axions, hypothetical particles with unusual properties. Another possibility is that gravity behaves differently on large scales than we expect, requiring modifications to our theories. Experiments deep underground, in space, and at particle accelerators all search for signs of dark matter, but so far it has remained elusive. Its invisibility is stubborn. We see its fingerprints everywhere, but never the hand itself. For the Milky Way, dark matter's influence is practical as well as profound. Without it, the sun would not orbit as it does. The spiral arms would not persist. The halo would not exist. Dark matter's gravity binds the galaxy. holding together the hundreds of billions of stars that would otherwise drift apart. The galaxy spins without falling apart because of this hidden mass. Every motion we observe, every rotation curve we plot, every stream we map in the halo is shaped by the invisible hand of a dark matter. From Earth, of course, you cannot see dark matter directly. The night sky shows only stars, planets, and nebulae. Yet once you know about it, the way you imagine the galaxy changes. Every star you see is only part of the picture. Surrounding it is an unseen halo, a cocoon of gravity holding it in place. The Milky Way becomes more than the band of light in the sky. It becomes a layered structure, luminous on the inside, invisible on the outside, woven together by something we do not yet understand. Dark matter also influences the Milky Way's interactions with its neighbours. The dance of dwarf galaxies around us is guided by the shape of the halo. Streams of stars from disrupted companions trace the invisible distribution of dark matter, bending along its contours. Even the future collision with Andromeda will be shaped by the halos of both galaxies, their invisible hands reaching out long before their visible disks touch. The Milky Way is not just a collection of stars drifting in space. It is an object defined as much by the unseen as by the seen. Some astronomers describe dark matter as scaffolding, others as glue, others as the cosmic web's foundation. However you imagine it, the message is the same. It is indispensable. Galaxies are not random collections of stars. They are bound structures, formed and sustained by invisible mass. Without dark matter, the universe as we know it could not exist. The fact that we do not yet know what it is does not diminish its reality. Its effects are written across the cosmos in motions, distributions, and patterns that cannot be explained otherwise. The search for dark matter continues, both in the heavens and in laboratories on Earth. Telescopes scan for annihilation signals, rare photons that might be produced if dark matter particles collide. Underground detectors watch for faint recoils, hoping to catch a passing particle. Colliders like the Large Hadron Collider probe high energies, looking for new physics that could reveal dark matter's nature. Each experiment adds to the hunt, even when results are null. The invisible hand remains hidden, but the pursuit itself is part of the story of how humans reach into the unknown. Meanwhile, astronomers continue to map the Milky Way's dark matter halo indirectly. Gaia's precise measurements of stellar motions help trace the gravitational potential, revealing how mass is distributed. Simulations compare those observations to models, testing different shapes and densities. The result is a picture not yet complete but increasingly detailed. A vast halo, extending far beyond the stars, guiding their paths in silence. For those who prefer to think in metaphors, dark matter is like the stage on which the galaxy's play unfolds. The actors, the stars, planets, and nebulae, are visible. The stage itself is hidden, yet without it the play could not exist. The invisible hand of dark matter shapes every movement, every orbit, every spiral. It does so quietly, without fanfare, without light, but with irresistible gravity. And while the mystery remains, there is comfort in the fact that we can at least see its effects. The Milky Way spins steadily, its arms curl gracefully, its halo extends broadly, all because of dark matter. Even if we never know exactly what it is, we can still appreciate what it does. It is the unseen companion to every star, the hidden partner to every orbit, the silent architect of our galaxy. The Milky Way is a story of light, but also a story of darkness, and both together create the structure we call home. When you picture the Milky Way, it's easy to imagine the galaxy as a vast collection of stars spread across majestic spiral arms, wrapping outward from a dense, glowing centre. Somewhere in that immensity is the Sun, but the question of exactly where we are in this grand structure is both humbling and fascinating. Our solar system does not sit in a prominent location, nor on one of the great sweeping arms that define the galaxy's spiral shape. Instead, we occupy a modest spur, a smaller branch that stretches between two larger arms. It is sometimes called the Orion Arm, or the Orion Spur, and this is our cosmic address in the Milky Way. The Orion Arm is not one of the galaxy's major arms like Sagittarius or Perseus. It is more like a side road branching between two highways, a lane that lies between greater routes of stars and gas. It extends for a few thousand light years, containing a mixture of stars, nebulae, and clusters. From within, it feels immense enough. After all, even the nearest stars are light years away, and the Orion Arm itself is thousands of light years across. But compared to the galaxy as a whole, it is small, just one feature among many, easily overlooked on a grand map. Yet this small spur is our home. The Sun, Earth, and everything familiar resides here, orbiting quietly within this narrow structure. Many of the constellations that dominate our skies are part of this same region. Orion, with its bright belt stars, gives the arm its name. Cygnus, Cassiopeia, and Perseus also trace regions of the Orion Spur. When you look at these constellations, you are seeing not just random patterns, but stars that share our spiral neighbourhood. They are local landmarks within the arm, guiding us through the galactic landscape. Being on a smaller spur has advantages. The larger spiral arms are crowded places dense with star formation, massive clouds of gas, and bright, short-lived stars. Such regions are vibrant, but they're also chaotic. Supernovae explode frequently, radiation levels are high, and gravitational interactions are stronger. Our Orion Spur is quieter, less intense. The Sun orbits in a relatively calm region, away from the hazards of the galactic centre and the turbulence of major arms. Some scientists suggest that this stability may have been important for the development of life on Earth. Had we been located in a more violent part of the galaxy, the conditions might have been less favourable. Still, the Orion Arm is not empty. Within it lie some of the most famous sights in the night sky. The Orion Nebula, a glowing cradle of new stars, is part of our local spur. The Pleiades cluster, bright and distinct even without telescopes, resides here. The Horsehead Nebula, the Rosette Nebula, and countless other clouds of gas and dust mark regions where stars are forming. These are not distant features glimpsed across the galaxy, but local neighbours, only hundreds or thousands of light years away. When you see them, you're looking into the very fabric of our own spiral arm. Our location also provides a vantage point. From the Orion Spur, we can look outward toward the Perseus Arm, seeing it across the gulf of space. We can also look inward towards Sagittarius, glimpsing the brighter, denser regions closer to the galactic centre. This position offers perspective, a view across the disk that might be less clear if we live deeper inside a major arm. From here, we can map the galaxy, measuring distances and motions, piecing together its structure. It is a modest place, but one well suited to observation. Over billions of years, the Sun has drifted through different parts of the galaxy. It has likely crossed spiral arms before, moving slowly relative to the density waves that define them. Each passage would have brought changes, nearby star formation, increased radiation, and perhaps gravitational perturbations. At present, we are between major arms, in a calmer region. But on cosmic timescales, this position will not last. The solar system continues its orbit, and in tens of millions of years, we may once again pass through a busier spiral arm. The Orion Spur is not permanent. It is part of the galaxy's ever-changing dynamics. To imagine our place on this tiny spiral arm is to imagine balance. We are small, yes, located on a spur rather than a grand arm, but that smallness has advantages. It has provided stability, quietness, and a vantage point from which we can study the galaxy. It is easy to wish for a more dramatic location, nearer to the centre or within a brilliant arm, but perhaps our modest address is precisely what allowed us to be here, reflecting on it. Astronomers have used our position to great advantage. From here, surveys like Gaia can map billions of stars, creating a three-dimensional picture of the Milky Way. Our relatively clear line of sight in many directions has allowed us to measure parallax and discover Cepheid variables, using them as stepping stones to greater distances. The Orion Spur is not just a home, it is a platform for discovery, enabling us to look both inward and outward, to trace the galaxy's form from within. On a personal level, our place on a tiny spiral arm also offers perspective. The stars that seem scattered randomly across the night sky are, in fact, part of a structure, connected by their location within the galaxy. When you look at Orion rising in winter, you're seeing the luminous markers of the very arm in which we reside. When you see the Milky Way's band overhead, you're looking along the plane of the disk, peering through layers of arms and spurs. The sense of isolation that sometimes comes with thinking about space is softened by this awareness. We are not floating alone, we are part of a structure, bound into a spiral, orbiting with billions of other suns. And while the Orion Spur may not be one of the Milky Way's grand arms, it is no less rich in beauty. Its nebula, clusters and stars provide some of the most striking views in the sky. Its calmness has nurtured our planet. Its vantage point has allowed us to see and understand more of the galaxy than we might otherwise. Our place may be small, but it is not insignificant. It is part of the whole, one thread in the spiral tapestry of the Milky Way. So when you think of our location in the galaxy, picture not a lonely star adrift in blackness, but a star among billions, resting on a quiet spur between mighty arms. Picture the Orion Nebula glowing nearby, the Pleiades shimmering like jewels, the great arcs of Perseus and Sagittarius stretching beyond. That is our place, a tiny spiral arm, modest but steady, ordinary but essential. It is where we orbit, where we observe, where we reflect. And in its quiet embrace, life arose, consciousness emerged, and the universe learned to look back at itself. When we think about the Milky Way, it's easy to picture it as the whole of the universe, a grand island of stars stretching as far as our eyes and instruments can reach. But in truth, our galaxy is only one among many, a member of a family of galaxies bound together by gravity. We do not drift alone through the cosmos. Instead, we move within a group of neighbours, some small, some large, all orbiting, pulling and influencing one another across millions of light years. Chief among these neighbours is the Andromeda Galaxy, a system as vast and complex as our own, looming across intergalactic space. Together, the Milky Way and Andromeda form a pair, the two dominant galaxies of what we call the local group. Andromeda, also known as M31, is the nearest spiral galaxy to us, lying about 2.5 million light-years away. That distance sounds immense, and it is, yet on the scale of the universe, Andromeda is close. Its light, visible to the naked eye from dark skies, has travelled for millions of years to reach us, carrying with it the history of another galaxy. Through a telescope, Andromeda reveals its spiral arms, its bright core, its faint halo stretching farther than our eyes can follow. It is larger than the Milky Way, containing perhaps 1 trillion stars, and it is moving toward us at hundreds of kilometres per second. In billions of years, the two galaxies will collide, merging into a new system. The thought of two galaxies colliding might conjure images of stars smashing into one another, but space is so vast that direct star-to-star collisions will be rare. Instead, the galaxies will pass through one another, their gravitational fields tugging and twisting, pulling stars into new orbits, triggering waves of star formation, and eventually settling into a single, larger elliptical galaxy. Our solar system may be flung into a new region of space, or it may remain bound, circling a different centre. The night sky would transform, with Andromeda swelling larger and larger until the two galaxies blend into one. This future encounter is not something to fear. It is a natural step in cosmic evolution, one that has happened countless times across the universe. Andromeda is not the Milky Way's only neighbour. Alongside us in M31 lies the Triangulum Galaxy, or M33, a smaller spiral with tens of billions of stars. Though smaller, it is still impressive, and its connection to both Andromeda and the Milky Way is strong. Some astronomers think Triangulum may orbit Andromeda, while others see it as a separate member of the local group, bound by the combined gravity of both giants. Beyond Triangulum, the local group contains dozens of dwarf galaxies, many orbiting the Milky Way, others orbiting Andromeda, and still more drifting between. Together they form a loose cluster about 10 million light-years across, a neighbourhood within the cosmic web. The local group itself is not isolated. It is part of a larger structure called the local sheet, which in turn belongs to the Laniakea supercluster, a vast region spanning hundreds of millions of light-years. Within this supercluster, galaxies gather into groups and clusters, connected by filaments of dark matter and gas. Our galaxy is just one node in this network, tied by gravity to its neighbours, moving along flows that stretch beyond human comprehension. The universe is structured not as random scatterings, but as a web, with galaxies forming the bright points of intersection. The Andromeda Galaxy holds a special place in our imagination because it is one of the few galaxies visible to the naked eye. On a dark night far from city lights, you can see it as a faint smudge, an elongated patch just above the constellation Andromeda. To know that this smudge is another galaxy, larger than our own, filled with hundreds of billions of stars, is a humbling realization. You are looking across 2.5 million years of travel, catching light that began its journey long before humans existed. In that smudge is an entire world of worlds, a galaxy with its own spiral arms, its own clusters, its own history of star formation and collapse. Astronomers have studied Andromeda in detail, and comparisons with the Milky Way are revealing. Both are barred spiral galaxies, both have extended halos of dark matter, both host dozens of satellite galaxies. Yet Andromeda seems to have had a more violent past, with evidence of mergers that left ripples in its disk. Its halo is even larger than the Milky Way's, stretching outward for hundreds of thousands of light-years. Its globular clusters, streams, and satellite galaxies tell the story of its growth, just as ours do for the Milky Way. In many ways, Andromeda is a mirror of our own galaxy, a nearby example of what we might look like from the outside. Our relationship with Andromeda is not static. The galaxy is moving toward us, closing the gap slowly but steadily. In about 4 to 5 billion years, the two galaxies will meet. Simulations show that the first encounter will fling stars outward, warping the disks. Over the following billions of years, repeated passes will eventually merge the two into a new galaxy, sometimes called Milkomeda by astronomers. By then, the Sun may be nearing the end of its life, but Earth, if it still exists, would witness skies filled with unfamiliar patterns, arcs of stars stretched across the heavens. The galaxy we know today will not last forever. It is part of an ongoing story of change, where galaxies grow by merging with their neighbours. Beyond Andromeda, countless galaxies fill the universe. Some are small dwarfs, barely more than smudges of stars. Others are massive giants, with trillions of suns and sprawling halos. The Milky Way is average in many respects, neither the largest nor the smallest, neither the oldest nor the youngest. But it is our home, and its neighbourhood shapes its destiny. Our place in the local group means we are bound to Andromeda, fated to merge, part of a story larger than our galaxy alone. These galactic neighbours also remind us that the universe is structured hierarchically. Stars form galaxies, galaxies form groups, groups form clusters, clusters form superclusters, and all of it is connected by dark matter, stretching into filaments that link across cosmic voids. To think of Andromeda is not just to think of one neighbour, but of the entire network in which we are embedded. The Milky Way is not a solitary island, but part of an archipelago, tied by gravity and history to everything around it. From Earth, the night sky gives only hints of this structure. The Magellanic Clouds, faint smudges in the southern hemisphere, are the nearest dwarfs. Andromeda, visible as a smudge in the north, is the nearest giant. Beyond that, the other members of the local group are too faint to see without telescopes. Yet knowing they are there changes the meaning of the stars above. Every point of light belongs not only to the Milky Way but to a larger context, a family of galaxies orbiting together through space. The night sky is not just a canvas of stars but a window into a community of galaxies, each one immense, each one alive with stars, each one part of the same cosmic web. To reflect on galactic neighbours is to reflect on perspective. We are small within the Milky Way, smaller still within the local group, smaller again within the supercluster, and yet we are part of it all. Our galaxy's neighbours are not distant strangers but companions in motion, sharing gravitational ties and eventual destinies. When you look up and see the faint light of Andromeda, you're seeing one of those companions directly, connecting across millions of years to a galaxy that mirrors our own. And beyond Andromeda, there are others. The universe is filled with galaxies, more than we can count, stretching into the depths of space. Each one is a neighbour to some other, bound into groups and clusters, tied together by the invisible scaffolding of dark matter. The Milky Way is one among billions, part of a network that spans the cosmos. Our galactic neighbours remind us that the universe is not empty but full, not solitary but communal, not static but dynamic. The Milky Way, vast and complex as it is today, was not always this way. Like every galaxy, it has a history that stretches back to the earliest times of the universe, a story written in stars, gas, collisions, and the silent pull of gravity. To understand how the Milky Way was born, we must go back nearly 14 billion years to a universe that was far different from the one we see now. In those early days, there were no galaxies, no clusters, not even stars. There was only a hot, dense, rapidly expanding cosmos filled with hydrogen, helium, and traces of other light elements. From that beginning, structures like the Milky Way slowly emerged, shaped by physics, chance, and time. In the first few 100,000 years after the Big Bang, the universe was a glowing fog of particles and radiation. As it expanded, it cooled, eventually becoming transparent. Photons that had once been trapped began to travel freely, forming what we now observe as the cosmic microwave background. The universe was still nearly uniform, but tiny variations in density existed, seeded by quantum fluctuations stretched by inflation. These variations were small, differences of only 1 part in 100,000, but they were enough. Over time, gravity would amplify them, pulling matter into clumps that grew into the first structures. Dark matter played the leading role in this process. Though invisible, it made up most of the mass, and its gravitational pull gathered into halos long before ordinary matter could. These halos acted like wells, drawing in gas from the surrounding universe. As the gas fell in, it cooled, condensed, and eventually ignited the first stars. The Milky Way's earliest ancestors were not majestic spirals, but small protogalaxies, loose gatherings of stars and gas within dark matter halos. They were clumpy, irregular, and chaotic, merging frequently with their neighbours. The first stars were different from the ones we see today. Composed almost entirely of hydrogen and helium, with no heavier elements, they could grow much larger. Some may have reached hundreds of times the Sun's mass, burning furiously and dying quickly in violent supernovae. These explosions enrich the surrounding gas with heavier elements like carbon, oxygen, and iron, the building blocks of future generations of stars. In this way, the universe began a cycle of enrichment, each generation of stars seeding the next with more complex ingredients. The Milky Way's eventual formation depended on this process, for without heavy elements, planets like Earth could never exist. As billions of years passed, the small proto-galaxies merged and grew. Each merger added stars, gas, and dark matter to the growing system. The Milky Way began to take shape through this accumulation, becoming larger and more organised. Some of the ancient stars from those early fragments still exist today, found in the halo and in globular clusters. These stars are fossils, older than the disk itself, reminders of a time when the galaxy was still assembling. Their ages, more than 12 billion years, show that the Milky Way's roots reach back almost to the dawn of time. The process of growth was not gentle. Collisions between galaxies were violent events, stretching stars into streams, shocking gas into bursts of star formation, and sometimes feeding central black holes. Yet because stars are so far apart, they rarely collided directly. Instead, the overall structures merged, blending into larger holes. Over time, the Milky Way's bulge formed from these early mergers, a dense collection of old stars near the centre. The halo accumulated as well, populated with the remnants of devoured dwarfs. Slowly the galaxy's disk emerged, as gas settled into a rotating plane, cooling and forming new generations of stars. By about 10 billion years ago, the Milky Way was recognisably a spiral galaxy. It had a central bulge, a disk, and forming spiral arms. The Sun, however, had not yet been born. Our star would arise much later, about 4.6 billion years ago, when the galaxy was already mature. By then, countless generations of stars had lived and died, enriching the gas with heavy elements. The solar system's composition, its iron, silicon, oxygen and carbon, was the product of that long history. We are, quite literally, children of the galaxy, born from material forged in its earlier epochs. Evidence for the Milky Way's birth is preserved in its oldest stars and clusters. By measuring their ages, compositions and motions, astronomers reconstruct the timeline of formation. The oldest globular clusters, more than 12 billion years old, tell us that the galaxy's earliest building blocks formed soon after the Big Bang. The distribution of stars in the halo reveals past mergers, with streams tracing the paths of disrupted galaxies. The bulge holds stars with a wide range of ages, evidence of early chaotic assembly. Each part of the Milky Way carries a piece of its origin story, like chapters in a long history book. Computer simulations add another dimension to this understanding. By modelling the universe from its early conditions, astronomers watch virtual galaxies form under the influence of gravity and dark matter. These simulations show halos merging, gas cooling, disks forming, and spirals emerging. The simulated Milky Ways resemble our own, confirming that the processes we infer from observations are consistent with the physics of the cosmos. They also reveal subtleties, such as the role of feedback from supernovae and black holes, which regulate star formation and shape galaxies over time. The Milky Way did not grow in isolation. It was part of the local group from the beginning, interacting with its neighbours. Some of the dwarf galaxies we see today are survivors of that era, remnants of the small proto-galaxies that merged into larger systems. Others are newcomers, captured more recently. The dance of galaxies is continuous, and the Milky Way's birth cannot be separated from the environment in which it occurred. The cosmic web funneled gas into it, neighbouring dwarfs collided with it, and gravity tied it to companions like Andromeda. Our galaxy story is one thread in the larger tapestry of cosmic evolution. The central black hole, Sagittarius A, also traces its origin to the galaxy's early days. It may have begun as a smaller black hole, formed from the collapse of a massive star and grown over time by accreting gas and merging with other black holes. Its presence at the heart of the Milky Way is a common feature of large galaxies, suggesting that black holes and galaxies grow together. The hidden heartbeat of the galaxy has been there for billions of years, pulsing quietly as the Milky Way took shape around it. For us, thinking about how the galaxy was born is both scientific and personal. Scientifically, it explains the structures we see today. The disk, the halo, the arms, the bulge. Personally, it explains our own existence. The atoms in our bodies were forged in stars that lived and died long before the sun. The heavy elements in Earth's crust were scattered by supernovae billions of years ago. The very fact that life could emerge depends on the enrichment that occurred during the Milky Way's formation. We are not separate from the galaxy's history. We are part of it, direct descendants of its birth and growth. From Earth, we cannot see the galaxy's past directly. We cannot watch it form, cannot rewind the cosmic clock. But the evidence is all around us. In the stars, in the clusters, in the streams, in the gas, in the black hole at the centre. Each piece is a fossil, a record of how the Milky Way was born. By studying them, we reconstruct the story, not perfectly, but enough to glimpse the broad arc of history. From small clumps of gas and dark matter to a vast spiral galaxy, from primordial stars to a planet with life, the journey is astonishing. And the story is not finished. The Milky Way continues to evolve, shaped by mergers, star formation, and interactions with neighbours. Its birth was only the beginning of a long life, a life still unfolding across billions of years. To think about how the galaxy was born is also to think about how it will grow, how it will change, and how it will one day merge with Andromeda to become something new. The Milky Way's origin is not just in the past. It echoes forward into the future, carrying the legacy of its birth into what comes next. When we think of the Milky Way, it is often in terms of what it looks like now, the spiral arms curving gracefully outward, the dense bulge at the centre, the faint halo reaching into space. But galaxies are not static. They are evolving systems shaped by gravity, collisions, and the slow passage of time. Just as the Milky Way was born from smaller fragments billions of years ago, so too does it have a future written in the language of mergers. To understand what lies ahead, we need only look at the evidence already in motion, the paths of our galactic neighbours, the structure of the cosmic web, and the inevitability of gravity's pull. The most dramatic event in the Milky Way's future will be its collision with the Andromeda Galaxy. At present, Andromeda lies about 2.5 million light-years away, but it is moving toward us at more than 100 kilometres per second. Though that sounds fast, the distance is so great that the encounter will not happen for about 4 billion years. Still, on cosmic timescales, this is soon. The two largest members of the local group are on a collision course, destined to merge into a single galaxy. Simulations of this future show what will unfold. Andromeda will grow larger in the night sky over millions of years until its spiral arms dominate the heavens. Eventually the two galaxies will overlap, their stars flung into new orbits, their gas compressed into bursts of star formation, their halos blending into one. The word collision can be misleading because it suggests impacts between stars. In reality, the vastness of space means that stars will almost never collide directly. Instead, the gravitational fields of the two galaxies will interact, pulling and stretching, creating tidal tails and streams. Gas clouds, however, may collide, and these interactions will trigger intense periods of star formation, lighting up the merging galaxies with brilliant new stars. Over time, the chaotic structure will settle into a new form, most likely a giant elliptical galaxy. The spirals we know today will fade into memory, replaced by a smoother, rounder system. For our solar system, the outcome is uncertain. It could be thrown farther out into the galaxy's outskirts, carried along in the reshuffling of orbits, or it could remain relatively close to the new centre, continuing its quiet path. Either way, the Sun will be near the end of its life by then, expanding into a red giant and eventually shedding its outer layers. Earth, if it still exists, will not be habitable. For us, the merger with Andromeda is not a personal concern, but for the galaxy as a whole, it is the next great transformation, one that will shape its destiny for trillions of years to come. The Andromeda merger is not the only future event awaiting the Milky Way. Even now, smaller galaxies are falling in, merging with our halo. The Sagittarius dwarf galaxy is in the process of being absorbed, its stars stretched into a stream wrapping around us. Other dwarfs too are on paths that will eventually bring them into the Milky Way. Over billions of years, the galaxy will continue to grow through these smaller mergers, just as it has in the past. Each addition changes the shape of the halo, contributes stars to the disk, and leaves behind streams that can be traced for eons. The Milky Way's future is not a single collision, but a continuous sequence of interactions, each one leaving its mark. As galaxies merge, they also influence their central black holes. The Milky Way's Sagittarius A will one day encounter Andromeda's central black hole. When the two galaxies merge, their black holes will sink toward the new centre, orbiting each other in a decaying spiral until they merge into one even larger black hole. This event will release enormous amounts of energy in the form of gravitational waves, ripples in space-time that will travel across the universe. Though invisible to our eyes, such an event would be detectable by future instruments, a grand signal of two galaxies uniting. The merged black hole will then sit at the heart of the new galaxy, anchoring it as Sagittarius A, anchors the Milky Way today. The long future also extends beyond the local group. After the Milky Way and Andromeda merge, the resulting galaxy will continue to drift, along with Triangulum and the other dwarfs, as a bound system. Over tens or hundreds of billions of years, the local group itself may merge internally, forming a single massive elliptical galaxy. Beyond that, expansion of the universe will gradually carry more distant galaxies away, until only those bound in our local region remain visible. The far future universe will be emptier to observers inside, the wider cosmos stretched beyond reach by dark energy. The Milky Way's descendants will be alone with their closest companions, isolated in a growing void. Galactic mergers are not destructive in the way we sometimes imagine, but they are transformative. They recycle gas, redistribute stars, and build new structures. Without them, galaxies would not grow into the shapes we see today. The Milky Way itself is the product of countless past mergers, stitched together from fragments that collided long ago. Its halo is full of evidence of these events, streams of stars, globular clusters, and remnants of devoured dwarfs. The future will only continue this process, carrying the galaxy into new forms. It is worth reflecting that everything we see in the night sky is temporary. The constellations, so familiar and fixed to us, will change as the Milky Way evolves. Over millions of years, stars will drift into new positions, erasing familiar patterns. Over billions, entire arms will shift, new stars will form, old ones will fade, and the galaxy will alter its appearance. The eventual merger with Andromeda will erase the Milky Way as we know it, replacing it with something different, something larger and rounder. To think of the galaxy's future is to realise that even on scales so immense, nothing remains the same forever. The long future of collisions and mergers is not limited to our galaxy alone. Across the universe, galaxies collide constantly, especially in clusters where they are densely packed. Some of the most beautiful images captured by telescopes show galaxies in the act of merging, their arms twisted into arcs, their cores glowing with bursts of new stars. These images are windows into the Milky Way's future, previews of what will one day happen to us. They remind us that we're not unique, that our destiny is shared by galaxies everywhere, bound by the same laws of gravity and motion. Simulations allow us to watch this future unfold virtually. By modelling the motions of the Milky Way, Andromeda, and the other members of the local group, astronomers can predict the sequence of events. The first pass between the Milky Way and Andromeda will occur in a few billion years, followed by repeated encounters. Eventually, after several billion more years, the two will settle into a single system. The details vary depending on the initial conditions, but the broad outcome is always the same. Merger is inevitable. Watching these simulations, one sees the graceful dance of galaxies, slow but unstoppable, a ballet choreographed by gravity. On human timescales, the galaxy's future seems unimaginably long. 4 billion years is nearly 1,000 times the age of our species. Yet in cosmic terms, it is the next act in the story. The universe itself is 13.8 billion years old, so a few billion years more is just another chapter. The collision with Andromeda is not far away in the grand sweep of cosmic history. It is already written into the motions we observe, already unfolding in the slow drift of galaxies toward each other. Thinking about this future brings both awe and humility. The Milky Way, which feels so permanent and vast, is only temporary, just one form in an ever-changing cosmos. Its spiral arms, its bar, its halo, all of it will change. The future holds collisions, mergers, transformations. Yet at the same time, the forces that drive these changes are steady and reliable. Gravity is patient, pulling galaxies together across millions of years, shaping the future as surely as it shaped the past. So when you imagine the long future of the Milky Way, picture Andromeda growing brighter in the sky, spanning more and more of the heavens. Picture streams of stars pulled into arcs, gas clouds colliding and sparking new suns, black holes spiralling together. Picture the galaxy settling, merging into one, their past identities lost but their mass and stars preserved in a new form. The Milky Way story does not end with this future. It continues, transformed, part of a universe where nothing ever truly disappears, but everything changes. The galaxy is immense, measured in light years and trillions of stars, wrapped in halos of dark matter and streams of ancient mergers. To think about its size and its history is to think in scales that dwarf our lives, scales so large that numbers lose their grip on imagination. Yet somehow, within this immensity, something personal emerges. The story of the Milky Way is not only about the birth of stars and the motion of spiral arms, it is also the story of us, of the way atoms scattered across billions of light years and billions of years have come together to form living beings, reflecting back on the very galaxy that gave rise to them. At its heart, this story begins with stardust. The early universe contained only the simplest elements, hydrogen and helium, with traces of lithium. These were the raw ingredients of the first stars, but not enough to make planets, oceans, or living cells. The heavier elements, the carbon that forms the backbone of organic molecules, the oxygen that fills our lungs, the iron in our blood, the calcium in our bones, were all forged inside stars. They were created in nuclear reactions that fused lighter atoms into heavier ones, reactions that released the energy making stars shine. When stars reach the end of their lives, they scatter these elements into space. Smaller stars, like the Sun will one day, shed their outer layers gently, creating planetary nebulae. Larger stars die more violently in supernova explosions that spread their contents across light years. Even heavier elements, like gold, platinum and uranium, are formed in the rare collisions of neutron stars. These catastrophic events fling matter outward at near-light speeds, enriching the galaxy with ingredients that would otherwise not exist. Every atom in our bodies once passed through these processes. The nitrogen in our DNA, the phosphorus in our cells, the potassium that balances our nerves. All of it was cooked in stars that lived and died long before the sun. When we say we are made of stardust, it is not metaphor but fact. The Milky Way is the ancestor of every living thing on Earth, not in some abstract way, but in the literal transfer of atoms from stars to space to planets to people. Our solar system formed about 4.6 billion years ago, from a cloud of gas and dust enriched by earlier generations of stars. Gravity pulled the cloud together, spinning it into a disk. At the centre, the sun ignited, beginning its long life of fusion. Around it, planets coalesced from leftover material, colliding, merging and settling into orbits. Earth was one of these, formed from countless impacts, heated and reshaped until it cooled enough for oceans to form. In those oceans, chemistry stirred into biology, and biology grew into life. The atoms forged in the Milky Way stars became molecules, cells, organisms, and eventually beings capable of reflecting on their origins. This personal connection changes the way we think about the galaxy. It is no longer just a vast structure in the sky, measured in light years and masses. It is the source of our bodies, our breath, our thoughts. To look up at the Milky Way is to look at the place where your atoms were born. The stars are not distant strangers. They are family, predecessors in a long chain of cosmic recycling that made you possible. The scale of this connection is both humbling and grounding. On the one hand, it shows our smallness. We are one species on one planet, orbiting one star on a small spur of a spiral arm in a galaxy of hundreds of billions of stars. On the other hand, it shows our unity with the cosmos. We are not separate from it. We are part of it, made of the same materials, subject to the same laws, sustained by the same cycles. The galaxy is not out there, apart from us. It is in us, woven into every cell. When you breathe, the oxygen filling your lungs was created in a star billions of years ago. When you eat, the carbon in your food was once part of interstellar clouds. When you look in the mirror, the iron in your blood once flowed through the heart of a massive star. These are not poetic flourishes, but physical truths, direct links between the cosmos and your body. You are literally a piece of the Milky Way, a tiny fragment of its immense story, alive for a moment before returning your atoms to the cycle again. Even our awareness is part of this connection. The ability to think about the galaxy, to measure it, to imagine its shape, is itself a product of cosmic history. Neurons firing in the brain are built from atoms that once lay in the cores of stars. Consciousness is the galaxy reflecting on itself, matter that once burned as light now arranged in patterns that create thought. When you wonder about the Milky Way is, in a sense, wondering about itself. On the personal scale, this connection can bring comfort. In daily life, the universe can feel remote, distant, overwhelming. But to remember that you are stardust is to remember that you belong here, that your place in the cosmos is not an accident, but an outcome of its natural processes. The galaxy is vast, yes, but it is also home, and you are part of its fabric. Every star you see in the sky is kin. Every atom in your body has travelled through the same cycles that sustain galaxies. You're not outside looking in. You're inside, living as part of the whole. The history of the Milky Way is not just about structures and mergers. It is also about individuals, planets, ecosystems, organisms that arise within it. Each person carries a piece of that history, each life a unique combination of atoms and experiences. From the perspective of the galaxy, we are small, but from our perspective, the galaxy is immense, and yet the two are linked inseparably. The grand and the personal meet in the fact of our existence. When you look up at the night sky, try to imagine this connection. Picture the stars not only as distant lights, but as sources of the atoms that make you. Picture the Milky Way not only as a structure in space, but as your ancestor. Picture yourself as part of its cycle, a temporary arrangement of stardust that will one day return to the galaxy, to be part of something else. This perspective does not diminish you. It situates you, grounding you in a story larger than any individual yet intimately connected to each one. The personal scale is not about shrinking the galaxy to our size, but about expanding our sense of self to include the galaxy. It is about recognizing that your body, your thoughts, your life are all part of a chain stretching back billions of years, part of a network that spans light years. To live is to participate in the Milky Way's ongoing story, to carry its history forward, to reflect it back in the form of awareness. And in the end, that awareness may be the galaxy's most remarkable creation. Stars burn, galaxies merge, black holes grow, but none of those processes involves reflection. Only here, on one small planet orbiting one ordinary star, did matter organize itself into beings who can ask where they came from. The Milky Way gave rise to that, and through us, it knows itself in a way it could not otherwise. From stardust to us, The scale becomes personal, the immensity becomes intimate, the galaxy becomes not just our home, but our origin and our essence. As the night stretches on, the mind begins to drift, just as the Milky Way itself drifts through space. The galaxy has taken us on a journey, from its centre to its arms, from its halo to its neighbours, from its ancient birth to its distant future. But in these quiet moments, it is less about facts and figures and more about the feeling of belonging, the sense that you are lying beneath a sea of stars that stretches farther than sight, deeper than imagination, and yet somehow includes you completely. The Milky Way is not just overhead, it is the very material of your being, the cradle of your atoms, the silent companion of your thoughts. When you lie back and look at the sky, what you see is not only light, but history. Each star carries a message from long ago, each glow the end of a journey measured in light years. The band of the Milky Way itself is a kind of memory, a record of billions of suns woven together, their light overlapping to form a soft, hazy glow. To gaze at it is to see time itself stretched across the heavens, a reminder that the universe is always in motion, always carrying stories forward, and in the stillness of the night, it is possible to let that enormity wash over you gently, not as something overwhelming, but as something soothing. The galaxy is vast, yes, but it is steady. Its stars move in orbits that last for hundreds of millions of years. Its arms curl patiently, its halo stretches quietly, its neighbours drift slowly closer. Compared to the pace of human life, the Milky Way is unhurried. To rest beneath it is to feel that slowness, to match your breath to the rhythm of something far greater, something that will continue long after any single life. The sea of stars above can be imagined as a true ocean, each point of light a distant wave, each cluster a swell, each arm a current. We are suspended within it, floating as a small vessel on a surface that seems endless. And yet, within that endlessness, there is calm. The ocean of the galaxy is not stormy. It is balanced, held together by gravity, its motions harmonious. To think of yourself as drifting within it is to accept that you are carried, held in place, part of the flow. There is nothing to resist, nothing to fear. The galaxy holds you in its currents, and you move with it naturally. Sometimes, when we speak of cosmic scales, it can feel alienating. Numbers so large they lose meaning, distances so vast they feel empty. But when those same scales are viewed from another angle, they can feel protective. The galaxy is so large that your worries, your anxieties, seem tiny in comparison. Its age is so great that your troubles cannot weigh upon it. Its stability is so profound that it makes your place within it secure. The galaxy does not demand anything of you. It simply exists, steady, luminous, and wide, and within it you are free to rest. Imagine, if you will, the slow turning of the Milky Way. Not something you can see with your eyes, not something you can feel on your skin, but something you know is happening. The sun carries you around the galactic centre, once every 225 million years. Right now, at this moment, you're in motion along that path, a quiet traveller in a journey older than your species. The stars around you are fellow travellers, each on its own orbit, each guided by the same gravity. Together, billions of them, they form a dance that is patient and sure. To know this is to feel part of something continuous, something unbroken. The spiral arms that stretch through the galaxy can be pictured as waves of light. They are not fixed, but patterns moving through the disk, places where gas gathers and stars ignite. In time, they will shift, fade, and reform, but in this moment, they curl outward with grace. Our solar system rides between them, in a quiet spur, a lane of calm water between brighter currents. To drift here is to be sheltered, to live in a place where life has had the chance to emerge, where time has been given for thought to develop, for reflection to arise. Above you, the Milky Way may look like a streak, but if you could rise outside of it, you would see the full shape, a barred spiral stretching for 100,000 light years. The halo surrounding it would fade into intergalactic space, connecting to the local group, tying us to Andromeda, Triangulum, and dozens of dwarfs. Beyond that, clusters and filaments stretch outward, the web of the universe connecting everything. And here you are, one small being lying beneath it, looking upward, your awareness a spark within that immensity. The galaxy is vast, but within its sea, your spark glows, however briefly, however softly. As your thoughts slow, you might let yourself imagine floating upward into that sea, rising past the clouds, past the edge of the atmosphere, past the solar system itself, into the disk of stars. Around you, suns shine from every direction, more than you could count in 1,000 lifetimes. Nebulae drift as colourful clouds, clusters sparkle like jewels, streams arc gracefully across the halo. You drift farther, past the Orion spur, across the arms toward the centre where Sagittarius A anchors the galaxy. You do not rush. You float, carried gently, weightless, peaceful. The galaxy embraces you, not with touch, but with scale, with the sense that you are part of it completely. From this vantage, time seems to dissolve. The millions of years between orbits become as nothing. The billions of years of the galaxy's age feel like a single deep breath. The future collision with Andromeda is not a threat, but a continuation. Another chapter in the same endless rhythm. Galaxies merge, stars are born, stars die, black holes grow, and still the universe expands, steady and sure. In that rhythm, your own life finds context. Your days, your nights, your moments of rest are all small ripples in a sea that endures, and as you breathe slowly, the galaxy breathes with you. Each inhalation is like a spiral arm curling outward. Each exhalation is like the fading of a star, returning its material to space. You are synchronized with it, not separate, not alien. The galaxy is not above you, but within you. The stardust that forms your body is the same stardust that shines above, the same stardust drifting through nebulae, the same stardust that will one day form new stars, new worlds. To sleep beneath the Milky Way is to return to that cycle, to let yourself dissolve into its flow, to rest as part of its ocean. Drifting now, you can let go of the need to measure, the need to calculate, the need to hold the galaxy in numbers. The measurements matter, yes, but they are not the whole. The whole is too vast to be captured in data. The whole is felt in moments like this, lying beneath the night sky, imagining the sea of stars as your blanket. The galaxy is not something you must understand completely. It is something you can simply rest within, letting its vastness hold you, letting its calmness ease you, letting its silence quiet your thoughts. And so, beneath the galactic sea you drift, you breathe, you rest. The stars above are steady, the galaxy turns slowly, and you are carried within it. Tomorrow will come, and with it the world of waking life. But for now, the Milky Way is your horizon, your cradle, your ocean. Its light is soft, its embrace immense, its rhythm eternal. Let yourself drift with it, as countless stars drift, as galaxies drift, as time itself drifts forward. You're safe within it, a small part of something unmeasurable, a fragment of stardust resting beneath the galactic sea. Thank you for joining this quiet journey through the galaxy. We've wandered together across spirals and halos, through clusters and clouds, across time stretching from the birth of stars to the futures yet to come. Along the way, the Milky Way has shifted from being a distant band of light in the sky to something closer, something intimate, something you are part of at every level. The atoms of your body, the air you breathe, the very thought passing through your mind, all of it was shaped by the galaxy. carried from one generation of stars to the next until it arrived here, in you. As you rest now, let yourself hold on to that sense of belonging. The galaxy is immense, but you're not separate from it. You're within it, moving with it, orbiting as part of its rhythm. Each heartbeat, each breath, each drifting thought is carried in the same currents that guide the stars. The Milky Way is not outside looking in. It is your home, your origin, your companion. If you found this time soothing, if drifting through these ideas has helped you rest, you might consider joining again, returning whenever you need the calm of science told slowly, carefully, gently. You are welcome here any night, beneath the stars, beneath the galactic sea. For now, close your eyes if you haven't already. Let the weight of the day slip away. Let the quiet vastness of the Milky Way hold you. Sleep, like the galaxy, comes when you let go, when you allow yourself to be carried, when you trust that the universe continues its rhythm without you needing to do anything at all. Good night, and may the stars above and the stardust within keep you company as you drift into rest.